Hello, and welcome to this comprehensive preparation course for the HPE0-V25 exam. In this introductory chapter, we will establish the foundational knowledge needed to master hybrid cloud integration and architectural design. This is an unofficial, independently produced course. It is not affiliated with, endorsed by, or connected to Hewlett-Packard Enterprise, HPE, in any way. All trademarks, logos, and product names are the property of their respective owners. This course is meticulously designed to provide you with a high-density technical overview of the HPE ecosystem, ensuring you move beyond superficial memorization toward a functional understanding of hybrid cloud mechanics. We focus on the core competencies required to architect, deploy, and manage enterprise-grade infrastructures that thrive under the stress of modern, global data center demands. You will learn to navigate the complexities of software-defined control mechanisms, resource algorithms, and the lifecycle management of complex hardware environments. By internalizing these compressed specifications, you gain the confidence to implement resilient infrastructures that are both scalable and secure. This is an essential investment for anyone aiming to validate their expertise in HPE's sophisticated hybrid cloud portfolio. We will systematically cover the essential pillars of the exam objectives, starting from consumption-based IT models and extending deep into compute, storage, and networking architectures. You will gain exposure to the diagnostic telemetry and predictive modeling tools that separate reliable, high-availability deployments from mere conceptual test environments. We will rigorously examine how hardware compatibility and cryptographic baselines intersect with virtualized workloads and container orchestration. Every module is structured to refine your troubleshooting intuition, teaching you to interpret system logs and deployment metrics with surgical precision. This program is your definitive guide to mastering the heuristics of hybrid cloud deployment. I look forward to starting our technical journey together in the next lecture. Welcome back to our discussion on hybrid cloud architectures. In this chapter, we will master the foundational components of a robust hybrid cloud strategy, focusing on the mechanisms that enable seamless integration between on-premises infrastructure and public cloud environments. By the end of this module, you will possess the technical precision required to navigate complex HPE0-V25 exam scenarios and translate high-level design requirements into resilient, enterprise-grade deployments. A successful hybrid cloud strategy is rarely about managing two distinct environments, but rather about abstracting the underlying hardware to treat varied locations as a unified pool of resources. At the heart of this abstraction lies the requirement for consistent policy enforcement across physical data centers and cloud providers. When we speak of architectural constraints, we are primarily concerned with latency, data sovereignty, and the physical limitations of network bandwidth when moving workloads between disparate platforms. If you imagine an application moving from an on-premises ProLiant server to a cloud-based container instance, the integration metrics must remain transparent to the end user. This requires a strong reliance on software-defined control mechanisms that automate the provisioning process while respecting the hardware compatibility matrices defined by the vendor. Without these automated guardrails, the risk of configuration drift between your local and remote environments becomes unmanageable. Lifecycle management in this context involves far more than just updating firmware or patching operating systems. It demands a sophisticated approach to API utilization, where every configuration change is treated as an intentional, version-controlled event. By leveraging APIs, you enable programmatic control over resource algorithms, which in turn allows for dynamic scaling based on real-time demand rather than static, forecasted limits. These resource algorithms are the heavy lifters of your hybrid ecosystem, balancing the cost efficiency of cloud burst scenarios against the performance predictability of local compute resources. However, you must be realistic about scalability limits, as no system is truly infinite in its capacity to absorb load. Understanding where those thresholds lie is essential for maintaining system stability. When we integrate these systems, we naturally introduce complexities that necessitate a rigorous approach to fault tolerance. If an API call fails or a network link between the two environments drops, your architecture must be designed to fail gracefully, ensuring that your core service remains operational despite the disruption. Enterprise deployments also require a strict adherence to cryptographic baselines to ensure the integrity and confidentiality of data in transit. In a hybrid world, you are effectively extending your trust boundary beyond the physical walls of your data center, which makes encryption and identity management non-negotiable. This security posture must be complemented by a proactive diagnostic telemetry strategy. Instead of waiting for a system outage to occur, you should focus on predictive failure modeling, where data from hardware logs and network latency patterns informs you of impending issues before they cascade into service disruptions. Rapid remediation is then enabled by the same automation frameworks we use for deployment. By linking your telemetry back to your deployment templates, you create a self-healing loop that minimizes manual intervention. Internalizing these technical specifics is what separates the casual cloud user from a systems architect capable of handling the rigorous demands of global data centers. See you in the next lecture. Welcome back. Today we begin our exploration of the HPE GreenLake Edge to Cloud platform. This chapter provides the foundational architectural knowledge necessary to master hybrid cloud integration and service delivery. HPE GreenLake represents a significant departure from traditional capital expenditure models by shifting the focus toward a consumption-based cloud experience that spans from edge locations to the core data center. At its core, this platform acts as an abstraction layer that enables organizations to manage diverse infrastructure assets as a unified pool of resources. When we talk about integration metrics, we are essentially looking at how the software-defined control plane interacts with disparate physical or virtual hardware. You must understand that the platform relies on a sophisticated telemetry ingestion engine that monitors resource utilization in real time. This mechanism is not merely for reporting. It serves as the critical feedback loop that informs subsequent capacity planning and automated provisioning decisions. By decoupling the management plane from the underlying hardware, GreenLake allows for a consistent operational experience regardless of whether the workload resides on bare metal servers, containerized environments, or traditional virtual machine clusters. To effectively navigate the architectural constraints inherent in a GreenLake deployment, you should focus on the interplay between the hardware compatibility matrix and the software-defined control mechanisms. The agility of this model depends on the ability of the platform to abstract complex hardware configurations into consumable services. When configuring these architectures, practitioners often encounter challenges related to latency, bandwidth, and the cryptographic baselines required for data protection across hybrid links. The platform employs a hierarchical approach to resource algorithms, which determines how compute and storage capacity are balanced against the demands of the workloads hosted within the ecosystem. You must appreciate that scalability limits are often defined by the physical constraints of the local edge infrastructure, which then dictates how the control plane handles offloading or bursting to public cloud environments. Internalizing these configuration matrices is non-negotiable because the system relies on predefined thresholds to trigger automated scaling and lifecycle management workflows. Lifecycle management and fault tolerance constitute the operational backbone of the GreenLake experience, requiring a shift in how we approach maintenance and remediation. The system utilizes predictive failure modeling, which cross-references real-time diagnostic telemetry against historical performance databases to anticipate hardware degradation before it impacts service levels. This proactive stance is supported by a standardized API integration layer, which permits orchestration tools and external management platforms to interact with the environment programmatically. When a fault occurs, the remediation process leverages these same APIs to reallocate workloads or trigger hardware replacement protocols without manual intervention. By treating the entire hybrid environment as an integrated software entity, operators can maintain cryptographic integrity and performance consistency even under the rigorous stress conditions typical of modern enterprise data centers. Proper alignment with these best practices ensures that the architectural design stays resilient as the business requirement for hybrid cloud capacity grows over time. See you in the next lecture. Welcome back. And today we turn our attention to the fundamental shift toward consumption-based IT models. Consumption-based IT represents a strategic transition from capital expenditure models toward operational expenditure frameworks, specifically within the HPE GreenLake environment. While traditional procurement requires forecasting peak demand and purchasing hardware up front, a consumption-based approach aligns infrastructure costs directly with actual usage metrics. This requires a robust architectural integration where telemetry data provides the granular feedback loop necessary for automated billing and resource provisioning. You must understand that this is not merely a financial shift, but a technical one, requiring software-defined control mechanisms that communicate in real time with the central management plane. When we move these workloads to a hybrid model, the underlying hardware must remain agile enough to scale capacity up or down based on these observed usage patterns. Architects often find that the primary constraint is not the hardware itself, but our ability to map those specific usage patterns to the correct resource allocation algorithms. By leveraging these models, organizations can effectively mitigate the common pitfall of over-provisioning infrastructure that sits idle for the majority of its lifecycle. To implement this effectively, you need to be comfortable with the diagnostic telemetry that fuels the entire consumption ecosystem. These data streams act as the heart of the system, providing the necessary metrics for performance tuning and predictive capacity modeling. Throughout this lesson, I will walk you through the integration metrics required for the GreenLake control plane to accurately interpret your enterprise deployment. We will look at the specific deployment heuristics that govern how software-defined controllers negotiate resource availability against the scalability limits of a physical cluster. Effective lifecycle management in this context depends heavily on your proficiency with API utilization, which allows for the programmatic adjustment of resources as business requirements shift. We will also examine how fault tolerance is achieved when the infrastructure is constantly fluctuating. This requires a deep understanding of how containerized workloads and virtualized instances react to sudden shifts in the underlying pool of resources. Proper configuration of these metrics ensures that your cryptographic baselines are maintained even as the system dynamically adjusts to varying enterprise workloads. The complexity often arises when troubleshooting these environments, as the traditional view of a static server uptime no longer applies. When you observe anomalous behavior, you must look at the diagnostic telemetry and correlate it with the specific consumption metrics being reported by the control plane. We often see cases where predictive failure modeling identifies a hardware component degradation before it impacts the service, but the system must then rapidly remediate by shifting the load to a healthy node without violating the architectural constraints of the hybrid environment. This demands a mastery of the internal resource algorithms, as these dictate how your applications perceive bandwidth, storage latency, and compute cycles during the migration or scaling process. You should think of this as an iterative feedback loop where your configuration settings, such as hardware affinity or minimum threshold limits, directly determine the resilience of the system under stress. Balancing these diverse requirements for performance, scalability, and security forms the core competency needed to pass the exam and build robust, sustainable data centers. I look forward to discussing the next set of architectural principles with you. Welcome back. In this chapter, we explore the foundational as-a-service models that define modern hybrid cloud delivery. If you are looking to master the complexities of modern IT infrastructure, this module is your essential guide to understanding how to move from traditional ownership to flexible, consumption-based delivery. We will break down the technical nuances of service delivery models, ensuring you have the knowledge required to successfully pass the exam and deploy enterprise-grade solutions. You will learn to articulate the differences between various service tiers and how they integrate into broader hybrid cloud strategies. Investing your time here is the most direct path to gaining the expertise needed to navigate the current technological landscape. The shift toward as-a-service models is not merely a change in billing. It is a fundamental re-architecting of how we consume compute, storage, and networking resources in a hybrid environment. When we discuss infrastructure as a service, we are essentially talking about the abstraction of hardware via software-defined control mechanisms that allow for rapid provisioning and elastic scaling. Within the context of the HPE ecosystem, this means utilizing platforms that treat physical hardware as a pool of resources managed through centralized APIs. You must understand that the architectural constraints here are dictated by the underlying hardware compatibility. Yet the consumer perceives only a virtualized, consistent interface. Diagnostic telemetry becomes the primary tool for monitoring these services, as we no longer interact with hardware at the physical layer during daily operations. We rely on predictive failure modeling to ensure that the abstraction layer remains performant and reliable. often using rapid remediation heuristics to maintain service-level agreements. Platform as a service represents a further level of abstraction where the enterprise focuses on the application runtime environment rather than the underlying kernel or operating system patches. In a hybrid cloud, this creates a distinct separation of concerns where the service provider maintains the stack's integrity while the customer manages code deployment and lifecycle management. The critical technical parameter for success here is the effective utilization of API gateways to orchestrate resource allocation dynamically. You will find that scalability limits in these environments are often bound by container orchestration policies and the underlying container runtime performance. When designing for this, one must account for cryptographic baselines that secure data in transit within the service boundary, ensuring an end-to-end zero-trust posture. This necessitates a deep understanding of resource algorithms that distribute load across available nodes based on real-time consumption metrics. Failure to properly tune these parameters often results in latency bottlenecks that manifest as inconsistent application behavior under stress. Software as a service completes the model by providing fully managed applications accessed through standard web protocols, effectively offloading all infrastructure maintenance to the provider. In the enterprise space, this requires rigorous vetting of the integration points between the SaaS provider and your internal identity and access management systems. Your focus here is less on the performance of the software and more on the synchronization of data and the reliability of the interconnectivity between your private data center and the cloud provider. We look at integration metrics to ensure that data flows are not interrupted by network fabric instabilities or firewall security policies. The primary challenge in a hybrid implementation is maintaining data sovereignty and compliance while relying on outsourced platforms for core business functions. You need to be familiar with how these models interact with hardware-rooted trust mechanisms to verify the integrity of the data being processed. Ultimately, the objective is to ensure that the transition to any as-a-service model does not compromise the overall resiliency of the hybrid ecosystem. See you in the next lecture. Hello, and welcome back. In this chapter, we will master capacity planning basics to ensure your infrastructure architectures are both resilient and performant under heavy enterprise workloads. Building a robust hybrid cloud architecture requires a disciplined approach to capacity planning, moving far beyond simple guesswork or static calculations. We must treat capacity as a dynamic variable that interacts directly with your compute, storage, and networking resources across both on-premises data centers and public cloud footprints. When you look at HPE-focused deployments, you are primarily concerned with how resource algorithms negotiate demand against hard architectural constraints. A common pitfall is to over-provision hardware based on initial procurement budgets, which frequently leads to stranded assets and inefficiencies that complicate long-term lifecycle management. Instead, you need to internalize the relationship between peak performance requirements and the threshold of your hardware compatibility matrices. By understanding these limits, you gain the ability to predict how software-defined control mechanisms will react when a specific segment of your infrastructure approaches its performance ceiling. Successfully planning for capacity necessitates a deep dive into integration metrics that define how disparate hybrid environments communicate their status. You should focus on how diagnostic telemetry provides the raw data required for predictive failure modeling, which is a cornerstone of maintaining enterprise uptime. If you manage an environment at scale, you will quickly observe that cryptographic baselines and security overhead also consume measurable cycles, meaning your resource planning must factor in these hidden costs. Reliability hinges on recognizing the scalability limits of your chosen platforms, as pushing beyond these bounds often results in nonlinear performance degradation. We evaluate these factors by looking at deployment heuristics, which allow us to simulate workload behavior before committing to a specific infrastructure footprint. This methodical approach to resource allocation allows for rapid remediation should your telemetry indicate an impending failure, ensuring that remediation is proactive rather than reactive. When we discuss data storage within this context, we must consider the mechanical impact of condensed data features, such as deduplication and compression, on your compute load. While these technologies save valuable physical space, they operate on specific algorithms that require consistent CPU and memory overhead to function efficiently. Capacity planning is therefore not just about raw disk space or core counts, but about balancing these trade-offs against the latency requirements of your applications. In a hybrid world, you are often bridging the gap between high-performance local arrays and elastic cloud storage, meaning your API utilization must be precise to orchestrate data movement without bottlenecks. Furthermore, your architectural decisions regarding compute infrastructure must align with your long-term growth projections to avoid frequent and costly hardware upgrades. Achieving this balance requires a rigorous approach to analyzing your existing system logs to determine the actual utilization rates versus the theoretical maximums. Ultimately, becoming proficient in these basics allows you to navigate the complexities of HP integrated ecosystems with confidence. You are preparing to identify where scalability limits exist and how to best utilize software-defined tools to optimize your resource distribution. By internalizing these technical specifications, you define the quality of the service you deliver, keeping it within strict performance tuning boundaries. The goal is to establish a predictable, cost-effective infrastructure that can absorb fluctuating demand without compromising the integrity of your enterprise operations. Everything we discuss here supports the overarching need for resilience under rigorous stress conditions, which is exactly what the modern enterprise demands of its hybrid cloud strategy. Keep these principles in mind as we progress, as they form the foundation upon which your future technical design decisions will be based. See you in the next lecture. Welcome to the new chapter where we will analyze the technical frameworks and operational requirements of modern hybrid cloud ecosystems. By mastering these concepts, you gain the skills necessary to pass the HPE0-V25 exam and design robust, enterprise-grade cloud architectures. In this session, we investigate the fundamental mechanisms that govern hybrid cloud ecosystems. When we talk about an ecosystem in the context of HPE solutions, we are not simply discussing a collection of servers and storage arrays. Instead, we're looking at the intricate interplay between hardware-defined resources and software-defined control planes. Integration metrics serve as our primary signal for system health, requiring us to monitor the flow of data between on-premises assets and public cloud environment. We must account for architectural constraints that dictate how latency-sensitive applications behave when moved across these boundaries. It is essential to understand that integration is not a static state, but a continuous negotiation between available bandwidth and resource requirements. By formalizing these interactions, we create a predictable environment where workloads can transition seamlessly without compromising the integrity of the total system. Deployment heuristics provide the framework for how we distribute services within this architecture. Unlike traditional static environments, hybrid systems require us to think in terms of lifecycle management where resources are ephemeral. We rely heavily on API utilization to bridge the gap between disparate management consoles and centralized orchestrators. Resource algorithms determine the placement of these workloads, often prioritizing either cost efficiency or performance density based on predefined enterprise policies. When moving data, one must consider the cryptographic baselines that ensure security remains consistent regardless of the underlying physical substrate. If we ignore these baselines, we risk creating blind spots in our security posture that can be difficult to diagnose later under load. Maintaining a unified configuration matrix allows us to enforce these security standards systematically across every node. Scalability limits often become the first point of failure when an ecosystem experiences unexpected growth. We must distinguish between the theoretical maximums provided by hardware specifications and the realistic limits imposed by our software-defined control mechanisms. Performance tuning becomes a proactive task rather than a reactive one, focusing on identifying bottlenecks before they impact end-user experience. We utilize diagnostic telemetry to gain visibility into the health of all integrated components, allowing us to build predictive failure models. These models are invaluable because they allow the system to initiate remediation steps before a hardware component completely drops out of service. Rapid remediation is the hallmark of a resilient hybrid cloud ecosystem, and it requires engineers to understand how each telemetry stream reflects the underlying physical health of the infrastructure. Enterprise deployments rarely occur in a vacuum, meaning we must account for the rigorous stress conditions encountered in global data centers. When we look at fault tolerance, we are essentially building a safety net that accounts for asynchronous failures across different cloud providers and internal clusters. It is easy to overestimate the reliability of a link, yet we have to design with the assumption that connections will periodically fail. Our strategy revolves around state synchronization, which ensures that if an orchestrator experiences a failure, the new instance possesses an accurate representation of the current workload distribution. This level of synchronization relies on clean data and high-speed interconnects, which are foundational to maintaining a consistent hybrid experience. By internalizing these constraints, you are not just memorizing the exam syllabus, you are preparing to manage real-world systems with confidence. See you in the next session. Welcome back to this exploration of compute architectures, where we focus specifically on the HPE ProLiant Gen10 server series within the hybrid cloud landscape. Understanding ProLiant Gen10 servers requires more than just high-level familiarity. It demands a granular grasp of their specific engineering, designed to bridge the gap between traditional enterprise requirements and the fluid demands of hybrid cloud environments. These servers are built on the foundational principles of the Silicon Root of Trust, which establishes a cryptographic link between the hardware and the firmware, ensuring that the system will not boot if the code is compromised. This is a critical building block for security-conscious architectures that define modern enterprise infrastructures. When we integrate these into a hybrid strategy, we are essentially leveraging their predictable performance characteristics as the baseline for on-premises workloads that often serve as the anchor for public cloud migrations. The architecture utilizes Intel Xeon scalable processors, which provide the computational density necessary for virtualization and containerization workloads, essentially functioning as the engine room for the software-defined data center. By pinning down the exact hardware compatibility matrices and memory population rules, you gain the ability to predict the physical limitations of a cluster before you even commit to an infrastructure build. This predictive capacity is what separates a well-architected solution from one that simply grows organically until it hits an unmanageable performance bottleneck. The management of these servers is inextricably linked to ILO5, which represents a significant evolution in remote out-of-band management through its dedicated silicon layer. You must perceive ILO5 not merely as a management interface, but as an active participant in the server's lifecycle, providing the telemetry needed for health monitoring and fault tolerance. When considering deployment heuristics, we look at REST API integrations as the primary method for scaling configuration across a fleet of Gen 10 nodes, rather than relying on manual, console-based intervention. This shift to API-driven management allows for the standardization of security profiles, which is essential when enforcing cryptographic baselines across heterogeneous environments. If you are designing for resilience, you are looking at how these servers interface with storage and network fabrics through technologies like Gen 10 support for high-speed PCIe lanes, which directly influence data throughput in hybrid cloud scenarios. It is insufficient to view hardware in isolation. Instead, think of the ProLiant Gen 10 chassis as a programmable resource that exposes its operational state through diagnostic telemetry. This telemetry is what allows monitoring platforms to perform predictive failure modeling, enabling you to remediate hardware issues before they impact the availability of the host or the virtual machines running atop it. Scaling these systems effectively requires a deep understanding of the relationship between resource algorithms and hardware constraints, particularly during peak utilization periods. When a workload demands more compute cycles than a specific physical host can provide, the hybrid cloud model dictates that we should have defined mechanisms for bursting or offloading. But those mechanisms rely entirely on the physical node being healthy and properly configured. We manage performance tuning by adjusting power profiles and memory optimization settings within the BIOS, which are often codified into server profiles within management software to ensure consistency. These settings are not static. They represent the negotiated balance between electrical efficiency and the raw low-latency performance required by specific enterprise applications. Furthermore, the architecture supports diverse storage integration paths, including support for NVMe drives, which are essential for high IOP applications that might otherwise become the primary bottleneck in a cloud-connected architecture. By mastering the hardware compatibility lists and understanding the intricacies of the memory controller, you can avoid the common pitfalls of improperly balanced memory channels, which can significantly degrade performance in multi-node configurations. Troubleshooting at the Gen 10 level involves a disciplined approach to interpreting system logs and localized diagnostic information provided by the server's front panel status indicators and remote management reports. When a fault occurs, the goal is rapid remediation through the identification of specifically localized failures, such as a DIM error or a failing fan, without resorting to the destructive practice of replacing entire subsystems. You must familiarize yourself with the lifecycle management tools that allow for non-disruptive firmware updates, which keep the server aligned with the latest security patches and performance optimizations required by the broader hybrid ecosystem. These infrastructure components are designed to exist in a state of continuous improvement, where the hardware remains stable, while the software-defined control layer evolves to meet new operational demands. By internalizing these technical parameters and deployment heuristics, you move beyond simple hardware administration into the realm of structural architecture. This is the level of expertise required to justify your design decisions during the exam and in the field, ensuring that your enterprise deployments are both resilient and performant under the rigorous stress of modern production workloads. I look forward to discussing the next generation of computing in our upcoming session. Welcome to this lesson where we will explore the foundational technical architecture and operational specifications of ProLiant Gen11 servers. By the end of this session, you will grasp the critical design principles and management heuristics required to deploy these systems effectively within a hybrid cloud environment. The ProLiant Gen11 series represents a significant shift toward workload-optimized computing, moving beyond traditional general-purpose server design. At the core of the Gen 11 architecture is the focus on performance density, which is achieved through higher core counts and the integration of fourth-generation processors that support increased memory bandwidth. This shift mandates a deeper understanding of how these hardware resources interface with your software-defined control mechanisms. When evaluating the architectural constraints, you must consider the relationship between the processor topology and the internal I/O throughput. Since HPE is focused heavily on accelerating AI and data-heavy workloads, the Gen 11 design incorporates balanced PCIe Gen 5 lanes to ensure that high-speed networking and storage controllers do not encounter bottlenecks during peak utilization. This hardware-level optimization is the first step in ensuring your hybrid cloud infrastructure remains scalable and performant. Moving into the realm of lifecycle management, Gen 11 servers introduce enhanced telemetry capabilities that act as the primary interface for predictive failure modeling. Instead of reacting to hardware degradation, you are expected to leverage the underlying diagnostic data to engage in proactive remediation. This telemetry is not merely a collection of logs. It is a stream of structured metrics that integrate directly with management platforms to inform resource algorithms. Understanding how these servers handle state information is critical, especially when you consider that cryptographic baselines, such as the silicon root of trust, are baked into the hardware logic from the point of power on. You need to internalize the fact that security in the Gen 11 ecosystem is not an add-on, but a fundamental integration, where firmware immutability ensures that the platform initialization remains untampered throughout the server lifecycle. In terms of deployment heuristics, the configuration matrix for a Gen 11 environment has become more granular, requiring a shift in how you approach capacity planning. You should be familiar with the various chassis formats and their specific thermal envelopes, as these physical constraints directly influence your density calculations for a rack-level deployment. When you integrate these systems into a hybrid cloud fabric, the API utilization becomes the primary lever for automation. You will frequently interact with the RESTful APIs to push configuration baselines and align hardware states with your defined software models. This programmatic approach is what sets the Gen 11 apart from older generations. It is designed to be managed as code rather than as physical assets. Efficient management here relies on your ability to apply these baseline templates consistently across clusters, minimizing configuration drift that could otherwise compromise the stability of your enterprise workload. Troubleshooting within this ecosystem relies on the accuracy of your diagnostic telemetry. Because the Gen 11 servers utilize advanced silicon and granular sensors, you have access to a much higher resolution of performance data than ever before. If a workload experiences latency issues, your remediation strategy should start with an analysis of the system logs captured through the integrated management controller. By correlating these logs with your performance tuning parameters, you gain the ability to isolate transient microbursts that might otherwise look like hardware faults. Always remember that the goal is to map the observed telemetry back to the specific performance profiles you have established during the initial deployment phase. Maintaining this alignment ensures that your infrastructure remains resilient even under the rigorous, unpredictable stress conditions inherent in modern distributed data centers. I will catch you in the next session. Welcome back. In this session, we discuss Synergy Composable Infrastructure and how its architecture fundamentally alters how we provision data center resources. Synergy Composable Infrastructure functions as a fluid pool of compute, storage, and fabric resources that can be provisioned on demand through a single, unified interface. Unlike traditional siloed hardware architectures where physical server boundaries constrain resource allocation, Synergy treats every component as a discrete unit within a software-defined ecosystem. The fundamental mechanism here is the composable fabric, which allows you to decouple physical cabling from logical network configurations. By utilizing a unified API, administrators can compose a complex infrastructure stack, spanning servers, storage volumes, and network segments, in a matter of minutes rather than days. This level of abstraction is essential when you consider the requirements of modern hybrid cloud workloads that demand rapid elasticity. As an engineer, you should view this not merely as hardware, but as a programmable platform where the state of the infrastructure is maintained as code. When we examine the architectural constraints of the Synergy environment, we must focus on the role of the HPE OneView management layer. OneView provides the bridge between the physical hardware reality and the software-defined intent requested by the user. To achieve this, the system relies on specialized modules such as the Synergy Composer and the Synergy Image Streamer. The Composer acts as the brain, maintaining the hardware state and enforcing lifecycle management policies across the entire frame. The image streamer, conversely, allows for rapid deployment of compute nodes by streaming gold images to diskless servers, which drastically reduces the time required for OS installation and patching. Understanding this separation of concerns is vital for troubleshooting, as it allows you to isolate whether a failure resides in the orchestration logic or the underlying physical interconnects. You are effectively managing a system that treats hardware as disposable, ephemeral building blocks for your service deployments. Performance tuning and scalability within this environment hinge upon your understanding of the resource algorithms governing fabric utilization. In a Synergy deployment, the fabric modules connect to the frames, creating a non-blocking backplane that scales as you add additional frames to a logical pool. There is a density metric involved here, as you must balance the compute to storage to network ratio to avoid bottlenecks during peak demand periods. The system employs predictive failure modeling, which monitors diagnostic telemetry across all components to identify hardware degradation before it manifests as a service outage. If a storage module or a mezzanine card begins to exhibit anomalous behavior, the fabric intelligence can proactively migrate workloads or fence off the failing component without requiring human intervention. This capability is foundational to maintaining the high availability required by enterprise-grade hybrid cloud architectures. Security, specifically regarding the cryptographic baselines, remains a non-negotiable aspect of the Synergy ecosystem. Every node and module participates in a chain of trust that starts with the silicon root of trust embedded in the hardware. When you compose a resource, OneView validates the firmware state and security identity of the hardware before it is allowed to join the production fabric. This verification ensures that a rogue or misconfigured module cannot gain access to sensitive network segments. Furthermore, all API calls made to the management interface must be authenticated and restricted by role-based access control policies. As you prepare for your exams, remember that these security controls are not bolt-on features. They are intrinsic to the operational logic of the platform. Resilience is achieved only when the infrastructure remains in a known, secure, and measured state throughout its entire operational lifecycle. I will see you in the next lecture. Hello, and welcome back. Today we are exploring the architectural trade-offs between blade and rack servers within the context of mission-critical compute deployments. When we evaluate the deployment of compute resources in a modern data center, the decision between blade and rack architectures often dictates the operational efficiency and scalability of the entire hybrid cloud ecosystem. Rack servers, fundamentally designed as self-contained units, provide a degree of flexibility that allows for granular control over individual hardware configurations. Because each rack server possesses its own chassis, power supply, and cooling mechanisms, it operates as an isolated fault domain. This modularity means an enterprise can swap or upgrade a specific server without affecting the broader topology, which is a significant advantage in environments where heterogeneous hardware requirements are common. However, this independence manifests as a management overhead that increases linearly as you scale the physical footprint. You must contend with individual cabling for networking and power, which can lead to cable density issues that impede airflow and diagnostic efforts within the rack. In contrast, blade servers represent a shift towards centralized hardware abstraction and resource consolidation. By removing the redundant power and cooling components from every individual server node, blade systems utilize a shared chassis, often referred to as an enclosure or a blade center, to manage these externalities. This architecture is inherently more dense, allowing for a significantly higher compute per rack unit ratio, which is critical in space-constrained enterprise data centers. Integration metrics for these systems typically lean on backplane interconnects, where high-speed fabric modules handle networking and storage traffic, drastically simplifying physical cabling layouts. Yet, this high density introduces specific architectural constraints, particularly concerning thermal management and power draw thresholds. When you saturate a fully populated blade enclosure, you create a localized hotspot that requires sophisticated firmware-based airflow management to maintain operational stability and prevent thermal throttling of the underlying silicon. From a software-defined perspective, the management layer changes significantly, depending on whether you are running a rack-based or blade-based infrastructure. HPE OneView often serves as the orchestration engine here, but its interaction with these architectures is shaped by their distinct hardware realities. For rack servers, the focus typically involves individual ILO remote management sessions and independent configuration profiles, which can be time-consuming to synchronize manually across a large fleet. Blade systems, however, are designed for pool-based resource allocation where server profiles can be abstracted from the physical blades. This means you can easily migrate a defined identity or configuration from one blade to another within the same enclosure, which facilitates rapid remediation during firmware failures or hardware health alerts. This logical decoupling is a fundamental pillar of modern hybrid cloud integration, as it allows compute resources to be treated as ephemeral entities rather than fixed assets tied to their physical slot. Fault tolerance and diagnostic telemetry are equally critical when comparing these two form factors under rigorous stress conditions. Rack servers rely on localized health reporting, where diagnostic LEDs and direct board-level sensors provide the primary feedback loop for predictive failure modeling. While this is effective for isolating issues to a single machine, it lacks the broader context of the rack-level fabric. Blade deployments provide a more comprehensive, centralized telemetry suite, as the enclosure manager aggregates physical state data from all compute blades, storage blades, and interconnect modules simultaneously. This aggregation enables faster root cause analysis when identifying cascading issues, such as a failed high-speed fabric module that might otherwise appear as a collection of disjointed networking errors. You must ensure that your cryptographic baselines and firmware management policies are consistent across both models. Yet you will find that the blade enclosure often requires a more coordinated deployment strategy to avoid service interruptions during rolling firmware updates. Understanding these hardware primitives allows you to make informed decisions regarding workload placement and long-term capacity planning. A dense, uniform processing demand is almost always better served by a blade architecture, whereas unpredictable, niche, or specialized high-performance computing tasks may benefit from the individualized agility of rack servers. By mastering these distinctions, you align your infrastructure strategy with the realities of modern enterprise requirements, ensuring that your hardware remains an enabler for your hybrid cloud objectives rather than an artificial bottleneck. Your ability to distinguish between these deployment heuristics will directly influence the resiliency and maintenance lifecycle of the systems you oversee. Remember that there is no universal winner in architecture. There is only the right fit for the specific telemetry, density, and management requirements of your given operational environment. See you in the next lecture. Welcome back. In this session, we will examine the principles of firmware management as it applies to enterprise compute environments, specifically focusing on how these low-level components dictate the stability of your hybrid cloud. Firmware management is often relegated to a background administrative task, yet it is arguably the most critical layer in the hardware abstraction stack. At its core, firmware acts as the foundational software that provides low-level control for a device's specific hardware. When we talk about HPE compute architectures, we are essentially managing a complex interplay between the silicon root of trust, the integrated lights-out controller, and the server BIOS or UEFI. Ensuring these components are synchronized across a fleet of servers is not merely a maintenance exercise, but a fundamental requirement for security and stability. A mismatch in firmware versions across a cluster can lead to unpredictable behavior, especially when orchestrated through high-level software-defined managers. You must view firmware as a versioned artifact, much like the application code that resides on top of your virtualized or containerized infrastructure. Complexity of modern data centers forces us to adopt automated, repeatable processes for lifecycle management. Manually updating firmware on a single server is trivial, but when you are responsible for hundreds or thousands of nodes, you need a strategy rooted in firmware baselines. A baseline represents a known, tested, and approved state for your hardware components, covering everything from network interface card drivers to complex controller firmware. By defining these baselines, you shift the burden of compliance away from ad hoc updates toward a managed state that can be validated through diagnostic telemetry. Integrating these metrics into your hybrid cloud strategy allows you to predict potential hardware failures before they manifest as service outages. When you treat firmware as code, you gain the ability to version control your entire hardware stack, which is the only reliable way to maintain consistent performance tuning in a distributed system. Architectural constraints and hardware compatibility necessitate a strict adherence to interoperability matrices provided by manufacturers. It is a common mistake to assume that the latest firmware version is always the optimal choice for a specific production workload. Instead, perform thorough validation of the dependency chain, ensuring that the BIOS, ILO, and peripheral firmware are compatible with the specific OS kernel and container runtime you are deploying. This is where software-defined control mechanisms shine, as they allow us to orchestrate updates across an entire fabric without manual intervention. By using automated tools, you can implement rolling updates that preserve service continuity, effectively minimizing the impact of necessary maintenance windows. These heuristics of deployment are essential for enterprise deployments, as they enable you to scale your infrastructure confidently while remaining within the bounds of supported configuration parameters. Security, specifically the cryptographic baseline, must be integrated directly into your firmware management lifecycle. Modern HPE servers utilize a silicon root of trust, which creates an immutable fingerprint for the firmware before the system even begins the power-on self-test. If the active firmware has been tampered with or corrupted, the system will prevent execution, effectively stopping a compromised server from joining the network. This hardware-level protection is the bedrock of a zero-trust architecture, as it ensures that the lowest layers of the stack were not modified by malicious actors. You must understand how these cryptographic checks function in relation to your management APIs, as remote attestation becomes a core diagnostic capability. By monitoring these triggers, you can gain immediate insight into the security posture of your hardware across geographically distributed hybrid cloud sites. When looking at diagnostic telemetry, consider how firmware management integrates with predictive analytics platforms. These systems collect data points throughout the lifecycle of the hardware, analyzing subtle deviations in performance that indicate a failing component. If you are managing a large-scale environment, these predictive indicators become your primary early warning system for remediation. You should focus on understanding the thresholds that trigger these alerts, as they are calibrated based on specific hardware compatibility profiles rather than generic health checks. Rapid remediation requires a well-documented process for pushing updates to nodes identified by the analytics engine as having high failure probability. This closed-loop system is essential for maintaining the uptime guarantees expected in modern hybrid cloud ecosystems, where downtime is increasingly expensive and disruptive. Effectively scaling your compute infrastructure requires that you master the nuance of firmware behavior under rigorous stress conditions. Every component has inherent physical limits, and those limits are enforced or exposed by the firmware logic that manages resource allocation. During periods of peak load, firmware algorithms make micro decisions about power consumption, thermal throttling, and throughput, that can significantly impact the performance of your business applications. If your firmware is not correctly configured for your specific workload density, you may encounter performance bottlenecks that have nothing to do with your software stack. Therefore, optimizing firmware settings is a form of capacity planning that ensures your hardware performs predictably even when demand spikes suddenly across your hybrid environment. Internalizing these technical parameters is the difference between an administrator who reacts to failure and an engineer who designs for resilience. Through deep knowledge of your hardware stack and the tools that govern it, you can create a truly autonomous data center environment. The goal is to move as close to zero-touch management as possible, leaving the heavy lifting to the orchestration layers while you retain oversight through high-level telemetry. As you progress, remember that firmware is the layer that enables everything else. Treat it with the same rigor you apply to your application deployment pipelines. By mastering these fundamentals, you effectively eliminate a massive category of systemic risk from your production footprint. See you in the next lecture. Welcome back. Today, we are delving into the mechanics of compute infrastructure scaling to ensure your hybrid environments remain both resilient and performant. When we discuss compute scaling in the context of HPE solutions, we are essentially navigating the transition from static hardware allocations to dynamic software-defined resource pools. Scaling is not merely about adding physical nodes, it is about the intelligent orchestration of compute capacity to meet fluctuating application demands. In a hybrid cloud model, your ability to scale relies heavily on the abstraction layer provided by platforms like HPE Synergy or ProLiant-based composable structures. We must consider the architectural constraints inherent in our hardware, such as the maximum PCIe lane availability or the thermal envelopes of our rack deployments. These parameters dictate the upper limits of our scaling potential, necessitating a rigorous understanding of the underlying hardware compatibility matrices. Without this foundational knowledge, attempting to scale horizontally can lead to bottlenecks in the backplane or inefficient resource utilization. Integrating scaling mechanisms into a hybrid architecture requires a departure from traditional provisioning. We utilize software-defined control mechanisms to treat compute resources as abstract entities that can be invoked via APIs. This programmatic approach allows for lifecycle management that is both rapid and repeatable, which is essential when dealing with thousands of virtualized instances. The resource algorithms employed within these systems are designed to maximize density without compromising the fault tolerance of the individual host. When we talk about performance tuning, we are focusing on aligning the virtual machine requirements with the underlying compute hardware's capabilities to prevent resource contention. It is a balancing act of ensuring high availability while keeping cryptographic baselines maintained for every workload, regardless of its location in the cloud continuum. Diagnostic telemetry is the heartbeat of a scalable compute architecture, providing the visibility needed to make informed scaling decisions. We rely on predictive failure modeling to anticipate compute degradation before it affects the end-user experience, thereby allowing for proactive remediation. This telemetry feeds into the management ecosystem, enabling automated responses to events that would otherwise require manual intervention. Rapid remediation strategies, such as automated server reprovisioning or workload migration, are only effective if your infrastructure is designed with failover heuristics that align with your specific performance targets. You must be comfortable interpreting the system logs and metric outputs to discern the difference between transient spikes and genuine capacity saturation. By understanding these diagnostics, you ensure that your data center remains a coherent, responsive part of the broader hybrid ecosystem under varying stress conditions. See you in the next session. Hello. Today we are going to explore the technical foundations of HPE Alletra Architectures. This chapter focuses on high-performance storage delivery and the architectural mechanisms that enable cloud-like agility on premises. HPE Alletra systems represent a departure from traditional storage silos by utilizing a cloud-native data infrastructure that is managed through the HPE GreenLake edge-to-cloud platform. At its core, the architecture is designed to eliminate the complexity of managing disparate storage tiers, providing a unified experience that abstracts the underlying hardware complexity. We must view these systems not merely as arrays, but as programmable endpoints in a broader hybrid cloud ecosystem. The fundamental design philosophy centers on the decoupling of the control plane from the data plane, which allows for independent scaling and lifecycle management. When you examine these architectures, you will notice that the software-defined control mechanisms are the primary interface for orchestration, effectively shifting the management burden away from the physical hardware layer. This abstraction is critical because it allows enterprises to enforce consistent operational policies regardless of the physical location of the data. Understanding the performance profiles of Alletra requires a deep dive into the integration metrics and resource algorithms. These systems leverage non-volatile memory express as the primary protocol for communication, which significantly reduces latency by bypassing traditional bottlenecks inherent in older storage architectures. The hardware compatibility matrices are quite strict because the performance gains rely on the precise interaction between the flash media controller and the underlying NVMe storage fabric. You should familiarize yourself with the deduplication and compression engines, as these are not just optional features, but are hardware-accelerated components integrated directly into the data path. In these architectures, data reduction occurs in-line, meaning the processor overhead is minimized through dedicated silicon, ensuring that storage density does not come at the cost of input or output performance. When configuring these environments, you must account for the specific ingestion rates and the cache allocation heuristics to ensure that the storage fabric can handle the expected workload intensity. The fault tolerance and resilience mechanisms within the HPE Alletra ecosystem are largely defined by the architecture's reliance on predictive failure modeling and telemetry. Unlike legacy storage arrays that might rely solely on reactive snapshots or parity-based recovery, Alletra environments utilize advanced diagnostic telemetry to identify potential bottlenecks before they manifest as service impact events. This capability is deeply tied to the broader hybrid cloud integration, where aggregated metadata assists in forecasting capacity consumption and endurance limits. From a diagnostic perspective, the system treats performance degradation as a precursor to hardware failure, using algorithmic analysis to preemptively trigger live migrations or controller failovers. You must understand that these rapid remediation processes are handled by the software-defined controller, which orchestrates the movement of data blocks without requiring human intervention for routine component replacement. This level of autonomy is essentially what allows the architecture to meet the rigorous availability service level agreements expected in modern enterprise-grade data center deployments. In terms of security and deployment, the architectural constraints dictate strict cryptographic baselines that must be adhered to during the initial commissioning phase. Every Alletra system includes built-in encryption of data at rest, but the more critical aspect is the secure boot chain that ensures only authenticated, signed firmware can execute within the storage nodes. You will find that the integration of RESTful APIs into the lifecycle management flow is not just an administrative convenience, but a mandatory requirement for automating security updates and compliance auditing across a distributed infrastructure. If you are preparing for large-scale deployments, your focus should be on how these API endpoints allow for the programmatic definition of throughput limits and multi-tenancy quotas. By codifying these parameters, you effectively harden the infrastructure against unauthorized configuration drifts while ensuring that each workload resides within its intended performance boundary. Maintaining these cryptographic baselines while simultaneously managing the system through a centralized cloud console is the hallmark of a correctly architected storage environment. See you in the next session. Hello. Welcome back as we explore the core storage mechanisms within the HPE Primera ecosystem. In this session, we will examine the architectural foundations of the Primera platform, specifically focusing on its integration within hybrid cloud environments. We will analyze the underlying resource algorithms and the software-defined control mechanisms that dictate how this storage system handles mission-critical workloads. Understanding these components is essential for anyone aiming to pass the HPE0-V25 exam, as the platform represents a high-performance tier of the HPE storage portfolio. We will walk through the logic of its data reduction techniques and its capability to provide self-healing architectures. By the end of this discussion, you should be able to articulate why Primera is often the preferred choice for enterprise-level deployments requiring strict service-level agreements. It is not just about the raw hardware, but how that hardware interacts with the broader management ecosystem. The primary value proposition of the Primera architecture lies in its intent-based management, and its ability to decouple software innovation from hardware life cycles. When you look under the hood, you will find an all-flash architecture that utilizes a massively parallel multi-node structure. This design is focused on reducing latency while ensuring 100% availability, which is a bold claim, but one the system supports through predictive analytics and intelligent resource management. The software handles data placement across the controller nodes, ensuring that no single physical resource becomes a bottleneck during peak enterprise demand. This is facilitated by the ASIC-based storage architecture that offloads critical tasks, leaving the CPU free to handle complex, higher-level metadata operations. We often discuss efficiency in terms of condensed data, meaning the system is highly optimized for compression and deduplication without incurring a significant performance penalty on the host. In considering deployment heuristics, we must prioritize the integration of InfoSight into the management plane. This telemetry-based approach shifts the paradigm from reactive troubleshooting to predictive remediation, allowing the system to identify potential bottlenecks before they impact your applications. The integration metrics you need to monitor involve the API utilization patterns, which are central to how modern DevOps teams automate their storage provisioning. By exposing the storage capabilities via RESTful APIs, the Primera system inserts itself into broader infrastructure as code workflows seamlessly. Compatibility matrices for these systems are quite dense, necessitating a firm grasp of host-side requirements and fabric interconnectivity. You should view the storage fabric as a fluid entity where performance tuning is a continuous process rather than a one-time configuration event. Cryptographic baselines and security models within this framework are not merely add-ons, but are deeply rooted in the architecture to prevent unauthorized access and data tampering. The Primera ecosystem employs data-at-rest encryption as a standard practice, which is crucial for compliance with modern enterprise security mandates. When evaluating scalability, remember that the hardware limits are dictated by the node pair configuration, allowing for granular expansion as your capacity needs grow. The fault tolerance mechanisms here are robust, designed to survive multiple concurrent component failures without dropping a single I/O request. This resilience is a byproduct of the system's ability to reroute traffic dynamically when it detects a hardware fault or a degrading signal. Such rapid remediation is the heartbeat of what makes this platform suitable for the rigorous stress conditions present in globally distributed data centers today. See you in our next session on store architectures. Welcome to our deep dive into Nimble storage, where we examine the technical foundations that make this architecture a cornerstone of modern data management. We will explore how its specific design patterns and resource utilization strategies facilitate resilient, hybrid cloud-integrated storage environments. HPE Nimble storage architectures are fundamentally built upon the CASL or Cache Accelerated Sequential Layout file system architecture. This is not merely a marketing term. It represents a deliberate choice to decouple performance from capacity by using flash-for-read caching while writing data sequentially to disk. By transforming random write requests into sequential patterns before pushing them to the persistent storage media, the system significantly reduces the overhead typically associated with traditional RAID configurations. This architectural decision is what allows Nimble arrays to provide high IOPS alongside dense storage capacity without the typical performance degradation found in legacy spinning disk arrays. When you are analyzing these systems for your exam, it is vital to understand that the architecture is designed to prioritize data efficiency through inline, variable block, and sub-block deduplication techniques. These mechanisms operate in real time, meaning that the write path is optimized to verify and compress data before any bit hits the physical substrate. The efficiency of this process is augmented by the software-defined control plane, which allocates resources based on real-time telemetry gathered from the array's internals. In terms of hardware compatibility and deployment heuristics, understanding the controller's role is critical for any architect. Nimble controllers utilize an active standby model, but the software layer creates a near-instant failover capability that ensures high availability for the host applications. This design is focused on maintaining consistency during hardware state transitions, ensuring that the integration with hybrid cloud fabrics remains stable. When looking at scalability limits, we must distinguish between the physical shelf expansion and the logical grouping of arrays into larger clusters. Managing these scaling boundaries requires knowledge of the performance tuning parameters, particularly how the system handles cache misses and reads from the spinning disk layer. If the cache is correctly sized based on the working set of the workload, the system remains performant even under heavy stress. Furthermore, the cryptographic baselines are applied at the firmware level, ensuring that data at rest is protected without needing to offload encryption tasks to the host servers. This integration of security and performance is a hallmark of the Nimble ecosystem's approach to enterprise data services. Diagnostics and lifecycle management represent another layer of the Nimble architecture that demands your attention. The predictive analytics engine, which collects telemetry data, acts as a primary tool for fault tolerance and proactive maintenance. Rather than waiting for a hardware threshold to be crossed, the system uses diagnostic telemetry to identify patterns that precede drive failures or performance bottlenecks. You should internalize the concept of predictive failure modeling, as it directly impacts the service-level agreement metrics often debated in hybrid cloud environments. Rapid remediation is enabled by these automated feedback loops, where the array can signal for parts or trigger specific self-healing routines before a downtime incident occurs. API utilization is also a major component, as the RESTful interface allows for the programmatic management of snapshots, replication schedules, and quality of service policies. These APIs are essential for scripting, ensuring that the storage fabric can be treated as code, which is a requirement for modern infrastructure deployments in enterprise data centers globally. The complexity of these architectures can be managed by focusing on the relationship between the data path and the control path. While the control path handles management, configuration, and API requests, the data path remains focused strictly on the movement of bits and the maintenance of the file system integrity. Architectural constraints often arise when the ratio of flash to mechanical storage is unbalanced for a given workload type, leading to an over-reliance on the persistent storage tier for read requests. To overcome this, architects must understand the density configuration matrices provided in the technical documentation, ensuring that the chosen hardware model supports the expected throughput of the environment. If your workload involves significant deduplication or compression, the CPU overhead on the controllers must be accounted for within the resource algorithms of the system. Ensuring that these variables stay within predefined operational ranges is the difference between a resilient storage solution and one that risks bottlenecking under peak production pressure. By internalizing these technical requirements, you ensure that the hybrid cloud infrastructure remains stable regardless of the workload distribution. I will see you in the next lecture. Welcome back. Let us refine our understanding of how data efficiency is achieved through mechanical deduplication processes within enterprise storage. Deduplication technology operates by identifying and eliminating redundant data blocks within a storage system to maximize capacity utilization and reduce total cost of ownership. The process begins with the identification of data segments, where the system splits incoming data streams into variable or fixed-length chunks. Each chunk is then processed through a cryptographic hash function, typically SHA-256 or similar algorithms, to generate a unique digital fingerprint. These signatures are stored in a metadata index that serves as a lookup table for all existing blocks within the storage pool. When a new write request arrives, the system calculates the hash of the incoming data and compares it against the existing metadata database. If a match is found, the system simply creates a pointer to the existing physical block rather than writing the new data to the media. This effectively compresses the logical data footprint by ensuring that only unique instances of any information pattern occupy physical storage space. Over time, this mechanism significantly lowers the total IOPS required for data writes while introducing a computational overhead during the ingest phase. In hybrid cloud environments, architectural constraints often dictate where deduplication should occur, specifically distinguishing between inline and post-process implementations. Inline deduplication happens in real time as data is being written to the storage controller, which simplifies the process by ensuring space is saved immediately, but increases latency due to the CPU-intensive hash calculations. Conversely, post-process deduplication stores data in its native form initially and performs the deduplication scan during periods of low system activity. This approach minimizes the impact on application performance, but requires additional staging space to accommodate the redundant data before it is processed. Scaling these mechanics requires a thorough understanding of the resource algorithms involved, as the metadata index grows linearly with the number of unique blocks stored. If the indexing table exceeds the available cache or high-speed memory, the the performance of the deduplication engine degrades sharply, leading to bottlenecks that affect overall throughput. Consequently, enterprise architects must carefully balance the deduplication ratio against the latency requirements of the specific workloads running on the storage array. Integration metrics and deployment heuristics play a critical role in managing the lifecycle of deduplicated data across physical and software-defined storage layers. One frequently encountered challenge is the maintenance of data integrity when performing cryptographic baselines, as the risk of hash collisions must be mathematically eliminated by the storage controllers. The deduplication process must be fault-tolerant because a corruption in the metadata index could result in the loss of pointers to vast amounts of production data. Predictive failure modeling within these systems monitors the rate of incoming unique data versus redundant patterns to provide alerts when disk capacity is approaching its effective limit. API utilization allows administrators to query these metrics programmatically, enabling automated provisioning scripts to react when deduplication ratios fluctuate beyond established baselines. Furthermore, the mechanics must account for administrative tasks like snapshotting and replication, where deduplication can either drastically shrink the size of replicated sets or, if misconfigured, cause inflated data transfers across WAN links. Deep comprehension of these mechanics ensures that hybrid cloud infrastructures remain resilient even when operating under the rigorous stress of continuous, variable load enterprise data centers. I will see you in the next lecture. Hello, and welcome back. Today, we are diving into compression technology fundamentals, a cornerstone of storage efficiency within modern hybrid cloud architectures. In high-performance storage environments, compression serves as an essential mechanism for maximizing usable capacity while minimizing the physical footprint of data. At its core, compression operates by identifying redundant patterns within data blocks and encoding them more efficiently before they are written to persistent media. When dealing with HPE storage solutions, such as Alletra or Nimble, it is vital to distinguish between inline and post-process compression methods. Inline compression occurs as data enters the system, effectively reducing the logical capacity requirements before storage allocation occurs. This approach demands significant computational overhead, necessitating hardware-accelerated engines to prevent latency spikes during high I/O operations. Conversely, post-process compression performs the reduction after data has been committed to disk, which may offer advantages in write-intensive scenarios, but requires more available headroom on the underlying storage capacity. Understanding the architectural constraints of these mechanisms requires a clear grasp of how compression interacts with deduplication and encryption. Many engineers fall into the trap of assuming these processes are additive, but the order of operations significantly dictates performance outcomes. Generally, deduplication should be applied first to remove duplicate data blocks, followed by compression to shrink the remaining unique data, and finally, encryption to secure the payload. If you compress encrypted data, the entropy of the resulting stream often makes further effective compression mathematically impossible. Therefore, software-defined control mechanisms must be carefully tuned to ensure that the storage processor is not overwhelmed by the combined computational cost of these tasks. When designing for the hybrid cloud, we must also consider the performance impact on cross-site data movement, where compressed streams can significantly reduce the necessary bandwidth required between an edge site and the core data center. Integration metrics play a critical role when we evaluate the efficiency of a storage subsystem under stress. One primary metric is the data reduction ratio, which is not merely an indication of capacity savings, but a reflection of the workload's compressibility. Databases with highly structured schemas or log files often yield high compression ratios, whereas already compressed formats, such as JPEGs or encrypted backups, show minimal to no gain from further processing. From a lifecycle management perspective, we monitor these metrics via diagnostic telemetry to predict storage exhaustion thresholds more accurately. Modern HPE environments benefit from predictive failure modeling, where the system analyzes compression overhead trends alongside hardware resource utilization to provide alerts before performance reaches a critical degradation point. Predictive models allow administrators to scale capacity preemptively rather than reacting to storage failures caused by unforeseen workload shifts or rapid data growth. Hardware compatibility remains a fundamental constraint that dictates how effectively these compression algorithms operate at scale. Intelligent storage arrays use fixed-function hardware, such as FPGAs or ASICs, to offload compression tasks, freeing up system CPUs for higher-layer application logic. If you are operating within a virtualized or containerized ecosystem, the hypervisor's awareness of these storage-level features can impact how data is presented to the guest OS. When deploying applications that manage their own compression, such as modern distributed databases, you must ensure that hardware-level compression does not create a double compression scenario that wastes cycle time without providing additional space savings. Through correct API utilization, a software-defined storage management layer can intelligently toggle compression features based on the application profile and the sensitivity of the data being stored. Ultimately, the goal of mastering these compression fundamentals is to ensure resilient infrastructure that performs predictably under rigorous enterprise stress. By internalizing these configuration matrices, you gain the ability to troubleshoot performance bottlenecks by isolating the compression engine from network or host-side latency. During remediation, the ability to quickly toggle specific compression policies allows for rapid recovery when a sudden surge in ingest traffic threatens to saturate the storage controller's computational limits. This level of granular control is what separates manual configuration from automated, robust infrastructure management. As we look at the broader hybrid cloud ecosystem, the intelligence embedded within these compression engines serves to optimize not only our local storage costs, but also the total cost of ownership for data stored in distributed environments. I will see you in the next lecture. Welcome back. In this session, we will examine the technical underpinnings of storage fabrics and how these components facilitate connectivity within hybrid cloud environments. When we talk about storage fabric fundamentals, we are essentially discussing the high-performance interconnects that allow compute nodes to access storage arrays with minimal latency and maximum reliability. In the context of modern data centers, the fabric is not merely a collection of cables and switches. It is a complex, software-defined entity that dictates the efficiency of data movement. The primary objective is to create a non-blocking pathway that scales linearly with your business requirements. We must differentiate between traditional fiber channel fabrics and emerging NVMe over Fabrics implementations, as each imposes unique constraints on your architectural design. By understanding the mechanical reality of buffer credits and frame sizes, you move from simple configuration to sophisticated performance tuning. This level of technical depth is required to ensure that your storage throughput does not become a bottleneck for your high-performance workloads. Integration metrics are the benchmarks by which we evaluate the health and efficiency of a storage fabric. You cannot manage what you do not measure, and in hybrid cloud deployments, visibility must extend from the physical layer up to the storage controller orchestration. Consider the propagation delay introduced by distance in a stretched fabric configuration. This is a physical constant that software cannot always override. We often talk about predictive failure modeling as a means to mitigate downtime, but this relies heavily on telemetry ingested from the fabric switches themselves. When configuring these environments, you must account for the overhead of encapsulated traffic and the overhead of cryptographic baselines. These security measures are non-negotiable in enterprise settings, but introduce latency that must be factored into your performance heuristics. Balancing the need for absolute security with the operational requirement for low latency access is the mark of a skilled practitioner. Deployment heuristics provide a framework for scaling your fabric without violating your architectural constraints. When deploying a new storage fabric, it is easy to assume that plug-and-play simplicity applies, but enterprise hardware often requires manual tuning of queuing algorithms and flow control mechanisms. Scaling limits are often hit not because the hardware is insufficient, but because the fabric management logic becomes congested under specific traffic patterns. For instance, in a dense virtualized environment, the fabric may experience microbursts that overwhelm buffer caches if the congestion notification is not configured correctly. You must memorize and apply the configuration matrices provided by your hardware vendors, as these documents are the result of rigorous stress testing. Aligning your infrastructure with these tested best practices ensures that your fabric remains resilient even when facing the unpredictable loads of a modern cloud-native ecosystem. Finally, let us consider the vital role of lifecycle management and troubleshooting within the fabric. Diagnostic telemetry provides a real-time view of data integrity, allowing for rapid remediation before a failure impacts production services. Modern storage fabrics utilize RESTful APIs to automate the provisioning and zoning of storage, which effectively removes human error from the equation. However, API utilization necessitates a strong grasp of the underlying resource algorithms that govern path selection and load balancing. When troubleshooting a performance degradation incident, you should look for patterns in the system logs that correlate with fabric saturation or misconfigured multipath drivers. Consistent monitoring of these metrics forms the basis of a proactive maintenance strategy that minimizes risk. By grounding your expertise in these fundamentals, you maintain the rigor required for reliable enterprise infrastructure operations. See you in the next lesson. Welcome to this chapter on Aruba CX Switching, where we will examine the integration of high-performance network fabrics into hybrid cloud environments. Mastering Aruba CX is essential for anyone aspiring to certify in HPE hybrid cloud solutions, as it forms the networking backbone of the modern edge-to-cloud architecture. By completing this chapter, you will gain critical insights into how to leverage software-defined networking, optimize traffic flow in data centers, and manage complex switch deployments with precision. This knowledge is not merely theoretical, but is directly applicable to the rigorous requirements of the HPE0-V25 exam, ensuring you possess the technical depth to succeed. We focus on the design patterns and functional mechanics that set high-performing infrastructure apart from standard deployments. Investing your time here will clarify how network intelligence can significantly enhance your ability to maintain resilient and scalable cloud-ready environments. Aruba CX switching platforms operate on a fundamentally different premise than legacy hardware, primarily due to the AOS CX operating system, which is built on a microservices-based architecture. This allows for a modular approach where every switch process runs as an independent software entity, significantly improving fault isolation and system stability. When designing hybrid cloud solutions, you must account for the fact that AOS CX supports a REST API-centric management model, replacing traditional management constraints with dynamic, programmable interfaces. This transition to API-based control is vital for automating the deployment of network policies across geographically distributed sites. By utilizing the network analytics engine, practitioners can monitor and troubleshoot state changes in real time, which is a significant advantage when reconciling hybrid cloud storage and compute traffic. Understanding how these switches interact with the broader HPE portfolio is necessary for managing lifecycle operations, including firmware updates that are non-disruptive thanks to the underlying infrastructure's resiliency. Deployment heuristics in an enterprise context require a clear grasp of architectural constraints, particularly when bridging on-premises data centers with public cloud gateways. You need to consider the scalability limits of the switch fabric, which is often dictated by the specific ASIC architecture and the utilization of VXLAN and EVPN protocols for Layer 2 extension over Layer 3 boundaries. In a hybrid cloud environment, the ability to maintain consistent security and segmentation between virtualized workloads on compute nodes and physical switch ports is paramount. We observe that performance tuning of Aruba CX units involves detailed observation of packet buffering and queuing disciplines, especially during periods of high north-south traffic congestion. Furthermore, the cryptographic baselines applied to the management plane and data plane must align with current enterprise security standards, such as those defined in zero-trust frameworks. These specifications become the reference point for ensuring that the network remains performant under the stress of variable hybrid cloud workloads. Troubleshooting within this ecosystem shifts from traditional physical layer analysis toward diagnostic telemetry and predictive failure modeling. Because AOS CX provides granular access to system logs and state metrics via its integrated database, you can correlate network performance issues with specific application dependencies. Rapid remediation relies on the ability to query these telemetry streams using tools like the network analytics engine or external automation scripts. By building internal scripts to interact with the API, you effectively shorten the mean time to repair by detecting bottlenecks before they escalate into service outages. This proactive stance toward diagnostic management is exactly what is expected from infrastructure engineers operating within a consumption-based IT model. Remember that maintaining a high level of visibility through telemetry is the only way to ensure that your switch fabric scales linearly with the demands of your compute and storage backend. See you in the next part of the course. Welcome back to our exploration of modern data center infrastructure. Today, we are centering our discussion on the intricacies of software-defined networking within the context of HPE environments. Software-defined networking, or SDN, represents a fundamental shift in how we manage network connectivity by decoupling the control plane from the data plane. In traditional networking, every switch or router requires manual configuration of protocols and access lists, which becomes unsustainable in a large-scale hybrid cloud deployment. By abstracting the control plane into a centralized software controller, we gain the ability to manage the entire fabric as a single entity, rather than as a collection of discrete nodes. This is not merely an automation exercise. It is an architectural decision to enforce consistency across physical and virtual boundaries. HPE solutions leverage this paradigm to provide deep visibility into the flow of traffic, ensuring that policy enforcement remains uniform even when workloads migrate between on-premises servers and public cloud instances. When you architect for this shift, you are essentially defining the network's behavior through programmatic interfaces rather than physical toggles. The core of effective SDN implementation lies in the use of APIs and controller-based logic for lifecycle management. You must understand that resource algorithms within these controllers are responsible for path computation and load balancing based on real-time telemetry. In a hybrid cloud scenario, these algorithms must account for latency constraints and bandwidth utilization across disparate links. For instance, if you are stretching a layer 2 domain across geographic regions, the software-defined controller must identify optimal paths to mitigate hairpinning of traffic. Furthermore, the integration metrics you track, such as flow table occupancy and tunnel encapsulation overhead, determine the scalability limits of your infrastructure. Ignoring these metrics often leads to performance tuning bottlenecks that manifest during moments of acute traffic congestion or rapid workload scaling. Security within an SDN environment depends heavily on established cryptographic baselines for device authentication and data path protection. Unlike legacy systems, where port security might involve simple MAC-based filtering, modern SDN environments utilize certificate-based identity for every participating node in the fabric. This provides a resilient foundation that allows for the implementation of segmentation policies that follow the workload rather than the physical port. When dealing with diagnostic telemetry, you're looking for deviations in these traffic patterns that indicate either a malicious actor or a failed link within the overlay. Predictive failure modeling, which relies on the analysis of historical port counters and power consumption spikes, allows administrators to remediate issues before they manifest as outages. This is the cornerstone of building a resilient ecosystem that can withstand the rigorous stress of a global enterprise deployment. Hardened configurations and hardware compatibility matrices must be strictly adhered to during the deployment phase to ensure consistent behavior across the control plane. Many administrators make the error of assuming that all software-defined control mechanisms function identically across different versions of the underlying firmware. This is rarely the case, as the integration between the SDN controller and the hardware switches often relies on specific vendor-supported plugins. You should view these configuration matrices as non-negotiable requirements for stability. When you document your deployment heuristics, ensure that you account for both the primary controller and the standby nodes, as any mismatch in software versioning can lead to split-brain scenarios or unpredictable control loop behavior. Consistency at this layer is the only way to avoid the maintenance traps that often plague complex hybrid infrastructures. See you in the next lecture. Welcome back to our technical journey through the HPE hybrid cloud ecosystem. In this session, we will dissect core network topologies and their practical application within modern enterprise architecture. When we approach core network topologies, we are essentially defining the backbone through which all hybrid cloud traffic must transit. A robust topology is not merely a collection of cables and switches, but a structured architectural decision that dictates latency, throughput, and fault tolerance. In the context of HPE hardware and software-defined networking, we often move away from traditional tiered models toward leaf-spine architectures to serve the dynamic requirements of virtualized workloads. A leaf-spine design minimizes hops between any 2 points in the network, which is critical when latency-sensitive applications reside in a local private cloud while talking to resources in a public cloud. Understanding the constraints of these physical layouts allows us to better predict how data flows under heavy load. If you construct your topology without considering the oversubscription ratio between the leaf and spine layers, you will inevitably hit bottlenecks that no amount of software optimization can resolve. The integration of hybrid cloud necessitates that our core topologies are inherently scalable and software-aware. We utilize mechanisms like VXLAN and EVPN to abstract the underlying physical layer, creating an overlay network that remains consistent regardless of the hardware manufacturer. This approach provides the flexibility to move workloads between physical clusters without reconfiguring the underlying core topology every time a server is added or removed. We must maintain a strict awareness of the MTU settings across the fabric, as fragmented packets in an encapsulated network can cause severe performance degradation for heartbeat signals and synchronization tasks. Beyond the physical layout, the software-defined control plane provides the intelligence needed to orchestrate traffic based on application priority rather than just shortest path routing. By mapping our topology to the logical requirements of the business, we ensure that our resource algorithms have the headroom they need to rebalance traffic during failure scenarios. Scalability limits in core network topologies are tied directly to the hardware compatibility of the switching fabric and the management software's ability to handle complex routing tables. When we deploy Aruba CX solutions, for instance, we are operating within a framework that supports advanced diagnostic telemetry, allowing us to see exactly how traffic traverses the core in real time. This visibility is essential for predictive failure modeling, where we analyze patterns in packet loss or latency spikes before they manifest as a full-service outage. Effective lifecycle management in this environment requires that we treat the network as code, utilizing automated deployment heuristics to maintain consistent configuration baselines across all fabric nodes. If a switch upgrade or a firmware patch is applied inconsistently, the resulting drift in the topology can lead to asymmetric routing, which creates intermittent connectivity issues that are notoriously difficult to track down. Cryptography and security baselines must be embedded within the topology itself, rather than viewed as an optional layer added at the edge. Within the data center, high-speed encryption protocols are often offloaded to dedicated chips within the networking hardware to preserve processor cycles for application traffic. We must ensure that our design choices do not negate these cryptographic features, especially when implementing zero-trust architectures that verify every packet crossing the core boundary. When we integrate storage fabrics into the network core, the architectural constraints become even tighter, requiring dedicated traffic management policies to ensure that block storage traffic does not contend with routine management data. The goal is to create an ecosystem where the hardware and the software-defined control plane work in concert to provide a secure, high-performance path for all hybrid cloud workloads globally. By internalizing these compressed specifications and focusing on resilient infrastructure design, you prepare yourself to manage data centers that remain performant even under the most rigorous stress conditions. I will see you in the next lecture. Hello, and welcome back. In this chapter, we explore the complexities of network traffic management within hybrid cloud environments, focusing on how data flows across distributed architectures. We will examine the core mechanisms that ensure high availability and efficient resource utilization for enterprise-level deployments. Efficiently routing data across hybrid boundaries requires a firm understanding of how various components interact within a software-defined ecosystem. When we talk about traffic management, we are essentially discussing the orchestration of packet flow to maintain performance under rigorous stress conditions. An architectural constraint often emerges when we try to balance latency-sensitive traffic with bulk background replication, requiring us to implement sophisticated queuing and prioritization strategies. By leveraging software-defined control mechanisms, engineers can dynamically adjust these parameters based on real-time telemetry instead of relying on static, manual assignments. This level of automation is what separates a resilient, self-healing infrastructure from one that simply reaches a performance ceiling under load. In modern data centers, the goal is to keep the pipeline saturated without introducing the bottlenecks that lead to jitter or packet drop in high-density multi-tenant environments. Understanding the integration metrics is vital when transitioning workloads between on-premises assets and cloud endpoints. We have to consider how cryptographic baselines impact the overhead of traffic processing, as the encryption and decryption cycles consume cycles that might otherwise be used for packet traversal. When we evaluate scalability limits, we must account for the physical throughput of the fabric and the virtualized constraints imposed by the hypervisor or the container CNI. It is a common mistake to assume that simply adding more bandwidth solves performance degradation, as the root of the problem is often found in the algorithm that dictates how individual sessions are steered. Through intelligent utilization of APIs, administrators can programmatically define pathways that favor shorter hops or more reliable links based on current network health metrics. This enables a more granular level of control that mirrors the dynamic nature of contemporary application demands. Fault tolerance and predictive failure modeling are the final pieces of the traffic management puzzle. Diagnosing issues requires deep visibility into diagnostic telemetry, allowing systems to shift traffic away from failing nodes before an outage occurs. Rapid remediation relies on the capability of the network fabric to reconverge quickly, which is often dictated by the underlying protocol efficiency and the configuration of the logical topology. By internalizing these compressed specifications and hardware compatibility requirements, you ensure that the infrastructure remains compliant with best practices during stress scenarios. We are looking for consistency across the board, where the same logical policies apply regardless of whether the traffic is moving within a local rack or across an intercloud link. These patterns ensure that our architectures remain robust against the sporadic nature of network congestion and environmental inconsistencies encountered in global deployments. I will see you in the next lecture. Hello, and welcome to this session on data center fabric configuration. In this chapter, we explore the structural mechanisms and architectural constraints that define modern resilient network fabrics in hybrid cloud environments. When we talk about data center fabric configuration in the context of HPE solutions, we are essentially discussing the creation of highly available, low-latency interconnection layers that support modern hybrid cloud workloads. A fabric, by definition, is more than just a collection of switches. It is a unified, software-defined entity that manages traffic flow via specific heuristics to ensure load balancing and fault tolerance. In your preparation for the exam, you must move beyond simple connectivity and understand how these fabrics integrate with orchestrators like HPE OneView or Aruba fabric managers. We focus on how the control plane and data plane reside within these architectures to provide the density and performance required by enterprise applications today. The configuration parameters you encounter will often involve complex matrices that dictate how traffic is prioritized and how segments are isolated from one another in a multi-tenant environment. One of the foundational aspects of fabric configuration involves understanding how resource algorithms determine path selection across the internal switching architecture. When traffic moves from a compute node to a storage resource, the fabric must rely on deterministic routing protocols that minimize jitter and maximize throughput across heterogeneous links. You should think of this as an abstraction layer where the physical cabling is secondary to the virtual topology created by software-defined protocols. During the implementation phase, you are expected to manage lifecycle operations, which include updating firmware across the fabric without disrupting stateful connections. This requires a deep comprehension of how API utilization facilitates the automated deployment of these complex network states from a centralized management console. Integration metrics play a critical role whenever you are tasked with connecting your local fabric to external hybrid cloud services. The exam will test your ability to define the boundaries of a fabric, specifically how it interfaces with gateways that provide connectivity to cloud providers. You must consider the architectural constraints inherently imposed by the physical hardware and how these choices affect the scalability of your entire data center footprint. For instance, determining whether to use a leaf-spine architecture compared to a traditional three-tier model often rests on the specific performance tuning requirements of the workloads involved. When configuring these environments, you should be mindful of cryptographic baselines that ensure traffic remains secure as it traverses between the edge and the core. Troubleshooting within this ecosystem relies heavily on your ability to interpret diagnostic telemetry and apply predictive failure modeling. Instead of reacting to incidents, effective data center management requires you to monitor the fabric for anomalies and traffic patterns that might indicate an impending hardware degradation. Remediation strategies nowadays emphasize rapid, automated responses, which you can only configure if you have mastered the underlying logic of the fabric's reporting mechanisms. If an endpoint loses connectivity or experiences latency spikes, You need to be proficient in utilizing the API to pull historical logs that detail the exact state of the port and the associated workload. Understanding the relationship between these logs and the overall fabric health is a requirement for maintaining the resilient infrastructure the certification expects you to support. See you in the next lecture. Hello, and welcome back. In this session, we investigate the fundamental mechanics of network troubleshooting within the HPE hybrid cloud ecosystem, focusing on diagnostic telemetry and rapid remediation strategies. We often assume that our network topologies are static, yet in a hybrid environment, the interplay between on-premises assets and cloud resources creates complex, dynamic dependencies that require a disciplined approach to isolation and resolution. When we talk about troubleshooting, we are not merely looking for broken cables or failed ports, but rather analyzing the entire stream of telemetry data to discern whether a bottleneck is caused by latency, configuration drift, or perhaps an unexpected interaction between software-defined switching and physical hardware substrates. The goal is to develop a predictable methodology that relies on observable metrics rather than anecdotal evidence, ensuring that each intervention is grounded in the architectural constraints of the specific deployment environment. One of the most critical aspects of this process involves understanding how software-defined networking, or SDN, abstracts the underlying connectivity. Because the control plane is decoupled from the data plane, a fault in the management logic can manifest as a series of intermittent connectivity issues that appear to be physical at first glance. We must look at the API utilization patterns to confirm whether the fabric state is coherent across all segments. If your telemetry indicates an increase in packet drops, you first need to determine if this is a result of resource exhaustion at the edge, or if the policy enforcement points are incorrectly filtering legitimate traffic due to a misinterpreted cryptographic baseline. By consistently comparing current performance against established baselines, you can quickly identify anomalies that deviate from the expected operational profile of your enterprise infrastructure. Predictive failure modeling is another tool in our arsenal that allows us to move from passive resolution to proactive maintenance. Rather than waiting for a complete outage, we look at trend lines in our network congestion metrics and error rates to anticipate where the next failure might occur. This is particularly relevant when dealing with hybrid cloud integrations, where the connection between the private data center and public cloud providers might be subject to fluctuating bandwidth availability. By employing sophisticated heuristics, we can isolate whether a performance degradation is local to our internal switches or if it requires escalation with our connectivity provider, effectively saving us from wasting diagnostic efforts on components that are functioning within their defined parameters. This level of granular awareness is what separates a resilient, scalable network architecture from one that constantly oscillates between stability and crisis. Firmware and software versions also play a significant role in the stability of these environments, specifically when managing hardware compatibility within the Aruba CX Switching ecosystem. A minor mismatch in driver versions between a virtualized host and the supporting top-of-rack physical switch can cause subtle synchronization issues that evade standard interface down detection mechanisms. Therefore, when documenting your troubleshooting findings, always include the current firmware baselines and configuration matrix version as part of your initial investigation. This systematic approach confirms that you are not chasing ghosts in the machine while ignoring obvious configuration discrepancies that could be resolved with a simple update or patch application. Following these rigorous steps ensures that your infrastructure maintains its integrity even under the pressure of the rigorous stress conditions often encountered in high-load, modern data centers. See you in the next lecture. Welcome back. Today we examine the technical depth of HPE OneView as a central orchestrator within your infrastructure stack. HPE OneView represents the abstraction layer that enables software-defined management across your entire data center footprint. When we talk about it as a masterclass subject, we are not simply discussing a graphical user interface, but rather the underlying architectural principles that allow for declarative automation. At its core, OneView moves IT operations away from manual, imperative task execution toward a model defined by server profiles and templates. This shift is critical because it ensures that infrastructure consistency is maintained regardless of the underlying hardware generation. You are effectively managing state, where the desired configuration is defined in a profile, and the physical environment is brought into compliance with that definition by the management software. This mechanism is what allows enterprise environments to scale without incurring a linear increase in administrative overhead. To understand the lifecycle management capabilities, we must look at how the software interacts with firmware and hardware controllers. The platform utilizes firmware baselines to ensure that every server component, from the BIOS and ILO to the networking adapters, remains in a consistent state. This is vital when you are managing large clusters where configuration drift often leads to elusive, production-impacting bugs. By enforcing a firmware baseline, you eliminate the variance that otherwise plagues high-density compute environments. The system acts as a single source of truth, abstracting the complexity of intermodular communication. When a new hardware node is introduced or replaced, the profile is simply reapplied to the new physical entity, effectively decoupling the logical service identity from the specific hardware component it resides upon. Architecturally, we must address the integration metrics and resource algorithms that govern how OneView interacts with the broader hybrid cloud ecosystem. The platform exposes a comprehensive RESTful API, which is the primary interface for any serious integration with external automation tools such as Python scripts, Ansible, or custom portal frameworks. By treating your infrastructure as code, you can programmatically trigger scaling events or remediate configuration anomalies based on diagnostic telemetry. This API-driven approach is essential for modern data centers because it allows developers and operators to treat the hypervisor, storage, and networking layers as a unified, programmable pool of resources. You are no longer managing silos. You are managing a software-defined fabric where the programmatic interfaces dictate the flow of data and the allocation of capacity. We also need to contemplate the diagnostic capabilities and the predictive failure modeling that distinguish a robust implementation from a fragile one. The platform collects extensive telemetry data from the managed elements, allowing you to move from reactive maintenance to proactive remediation. This is driven by advanced heuristics that monitor the health of storage fabrics, power distribution, and thermal conditions across the rack. When the system detects a deviation from the established cryptographic baselines or performance boundaries, it provides actionable diagnostic data rather than just opaque error codes. This internal awareness allows for rapid remediation, minimizing mean time to repair during stress conditions. Essentially, your role is to configure these parameters such that the system acts as a self-healing entity, reducing the risk of downtime in mission-critical hybrid cloud deployments. I look forward to discussing how these concepts translate into practical application in the next session. Hello, and welcome. Today we are examining the mechanics of server profiles within the HP ecosystem. This chapter provides a concentrated look into managing infrastructure as code through abstraction. Server profiles represent the logical abstraction of a server's identity, effectively decoupling the hardware from the software configuration. When you create a profile, you are essentially defining a set of parameters that include BIOS settings, firmware baselines, boot order, and network connectivity, which can then be applied to any compatible physical hardware. This approach is fundamental to achieving agility in a hybrid cloud environment, as it allows your operations team to migrate workloads seamlessly across physical compute nodes without manual reconfiguration. The mechanism relies on an underlying model where the profile acts as a template, ensuring that consistent policies are enforced regardless of the server's chassis or slot placement. By defining these attributes centrally, you reduce the risk of human error during provisioning cycles, which is a common bottleneck in high-density enterprise data centers. You must view the profile as a declarative state that the management layer continuously monitors and reconciles against the current physical implementation to ensure strict compliance. Understanding the lifecycle management of these profiles is critical for maintaining infrastructure stability and scalability under stress. Once a profile is mapped to a server, the system manages the relationship through a defined state engine that tracks changes to both the hardware inventory and the profile configuration. Should a hardware failure occur, the administrator can move the server profile to a spare, healthy compute module, significantly reducing the recovery time objective. This portability necessitates a deep understanding of hardware compatibility requirements, as the profile expects certain base functionalities to be present, such as specific networking cards or storage controllers, to fulfill its configuration requirements. You should also consider the implications of firmware baselines assigned to these profiles, as they govern the software versions running on the hardware components. Keeping these baselines synchronized prevents the drift that often leads to unpredictable behavior during mass scaling events or heavy production load spikes. Architectural constraints and resource algorithms also play a significant role in how these profiles interact with the wider fabric. When you define network connectivity, you are essentially assigning virtualized identities to physical ports, which enables the orchestration of complex VLAN tagging or bandwidth shaping policies. The system utilizes specific heuristics to calculate the placement of these profiles, taking into account current resource utilization, power availability, and thermal constraints of the infrastructure. For highly regulated environments, the cryptographic baseline embedded within the profile, such as the utilization of the silicon root of trust, ensures that the server identity remains verifiable and secure throughout its operational lifecycle. Diagnostic telemetry collected from these profiles provides the raw data needed for predictive failure modeling, allowing you to intercept issues before they escalate into service outages. By mastering the API integration for these profile modifications, you unlock the ability to automate deployment at scale, treating your physical hardware as truly software-defined resources within your hybrid cloud fabric. See you in the next lecture. Welcome to our exploration of firmware management strategies. In this lesson, we will examine the mechanics of firmware baselines deployment and how they ensure infrastructure consistency across complex enterprise environments. Managing firmware at scale requires a shift from manual updates to a state-based configuration model. Firmware baselines represent a defined set of firmware and driver versions that are validated for a specific hardware target, ensuring that the entire compute environment remains in a known, stable, and supportable state. When we deploy these baselines, we rely on the logic provided by the service pack for ProLiant, which acts as the foundational repository for these validated releases. Instead of treating updates as individual patch cycles, we treat the baseline as the desired final state of the system, allowing the orchestration layer to calculate the delta between the current configuration and the goal. This reduction in drift is critical for large, hybrid, cloud-enabled data centers where manual inspection of every server is simply not feasible or scalable. Effective deployment heuristics begin with the creation of the firmware repository within your management platform. By importing the baseline metadata, you enable the system to perform a compliance scan against your existing infrastructure. This scan generates a comprehensive matrix detailing where components deviate from the established standard. We must understand that firmware baselines interact heavily with the underlying hardware abstraction layer, particularly when dealing with composable infrastructure. The deployment process itself must respect architectural constraints, such as the dependency between BIOS settings and peripheral firmware, to prevent inconsistent state transitions. If you attempt to update component firmware while ignoring dependent microcode versions, you risk triggering a boot failure scenario that requires physical intervention. Integration metrics play a vital role when we discuss software-defined control mechanisms in a hybrid context. As we push these baselines, we integrate diagnostic telemetry to verify that the target hardware has successfully applied the update without impacting availability. This involves monitoring the lifecycle management states through the Management API, which provides real-time status updates on the installation progress. If a deployment fails due to a resource constraint, such as an exhausted temporary storage partition on the integrated management processor, the orchestration agent should trigger a rollback heuristic. Understanding these failure modes allows us to design more resilient deployment schedules that account for maintenance windows and workload migration patterns. We aim to keep performance tuning consistent, as firmware versions directly influence the efficiency of data packet processing and power management algorithms. Security is an inseparable component of any baseline discussion, especially concerning cryptographic integrity. Firmwares must be verified against their cryptographic baselines to ensure the code has not been tampered with throughout the supply chain or during transmission. This aligns with the silicon root of trust, where the hardware verifies the firmware before initialization, ensuring that only authentic, signed firmware executes on the processor. When deploying updates, the management tool must validate these digital signatures to maintain the chain of trust established at the factory level. This is not just a configuration detail. It is a fundamental requirement of a zero-trust architecture. Neglecting the verification process during a mass update could inadvertently bypass years of security hardening. leaving the data center vulnerable to rootkits or compromised runtime environments. Troubleshooting is where theory meets the reality of heterogeneous hardware ecosystems. When a baseline deployment fails, we utilize diagnostic telemetry to isolate the root cause, looking for specific error codes or timeout patterns in the management logs. Predictive failure modeling within the system might flag a component as failing if the firmware update triggers excessive thermal interrupts or non-responsive cycles. Rapid remediation involves reverting to the last known good configuration or isolating the offending node from the cluster state to prevent the error from propagating further. Engineers should focus on interpreting these telemetry streams to identify whether the issue stems from a network constraint between the manager and the node or a physical compatibility mismatch. Mastering these diagnostic capabilities ensures that the infrastructure remains resilient even under the high stress of global data operations. Until we meet again. Hello, and welcome to this session focusing on the practical application of deployment templates within the HPE ecosystem. We will examine how these templates act as the structural blueprint for automated infrastructure lifecycle management. Deployment templates represent a fundamental shift from manual, repetitive configuration tasks to a cohesive, repeatable architectural state. When we look at HPE management environments, we see that these templates function as snapshots of an ideal configuration, encapsulating everything from BIOS settings and boot sequences to specific firmware versions and network connectivity requirements. The primary mechanism here involves a logical separation between the hardware identity and the desired state configuration defined within the template. By decoupling these elements, you gain the ability to apply a uniform configuration across diverse physical hardware, provided that the underlying compute nodes meet the baseline compatibility requirements. This approach mitigates the risk of configuration drift, which is an increasingly common issue in modern, high-density data centers. Every parameter you include in a template, whether it relates to RAID initialization or ILO security settings, is treated as an immutable instruction set during the instantiation process. Consequently, the reliability of your infrastructure is directly tied to the rigor with which you define and maintain these templates over time. Integrating deployment templates into your broader hybrid cloud strategy requires a clear understanding of the hardware abstraction layer. These templates do not operate in a vacuum. They interact heavily with the control plane to ensure that resource algorithms remain optimized for your specific workloads. For example, when you perform a mass deployment of server profiles based on a single template, the system evaluates logical constraints, such as power consumption envelopes and thermal thresholds. This is where architectural constraints become critical to the success of your implementation. If a template specifies a configuration that exceeds the operational parameters of the target hardware cluster, you are effectively introducing a point of failure before the server even begins production work. You must evaluate the integration metrics carefully, ensuring that your storage fabrics and network settings align perfectly with the target server's NIC and HBA capabilities. A template often contains compressed specifications that, while convenient, require a deep knowledge of the underlying physical constraints to troubleshoot effectively when deployment timeouts or logical errors manifest. Managing the lifecycle of these templates demands a structured approach to performance tuning and security baselines. Because deployments are often automated, any flaw within the template design will be replicated consistently across the entire fleet, resulting in what we might call a systemic misconfiguration. It is essential to integrate these templates with cryptographic baselines that ensure secure boot sequences and encrypted management traffic, rather than relying on legacy default settings. As you scale your environment, you will find that these templates become the mechanism for enforcing software-defined control, allowing you to iterate on your hardware configuration as easily as you would modify code in a source control repository. Furthermore, troubleshooting errors within the deployment workflow depends on your ability to interpret diagnostic telemetry generated by the management controllers during the profile application phase. If a server fails to apply a template, the logs will provide specific feedback regarding hardware compatibility or communication failures, and your success depends on your ability to perform rapid remediation. Predictive failure modeling within the platform can often alert you to hardware bottlenecks before you attempt to push a template change. but you must actively monitor these telemetry streams to gain that visibility. Ultimately, the use of deployment templates is about building resilience into the very fabric of your data center by ensuring that every system component is defined by a tested and verified blueprint. See you in the next lecture. Welcome back. In this session, we will examine the integration of REST APIs within the HPE management ecosystem to facilitate automated control of hybrid cloud resources. Building resilient enterprise infrastructures requires a shift from manual intervention to programmatic interaction, and the REST API serves as the primary conduit for this evolution. When we discuss REST API integrations, we are looking at a stateless architectural style that leverages standard HTTP methods to achieve granular control over compute, storage, and networking layers. For the HPE portfolio, this implies using standardized interfaces to push configuration changes, monitor resource consumption, and trigger lifecycle management events across disparate hardware platforms. Unlike proprietary command line tools that often vary by generation, a RESTful approach enables a consistent programmatic contract that remains stable even as the underlying firmware or hardware evolves. We essentially treat infrastructure as a software-defined asset, where the desired state is defined through JSON or XML payloads directed at the API endpoint. Understanding the underlying transport security, such as TLS 1.2 or 1.3 requirements, becomes as critical as the configuration metrics you are pushing to the controllers. Effective integration necessitates an understanding of the relationship between request methods and resource lifecycle states within the HPE environment. A GET request is your primary instrument for diagnostic telemetry and resource discovery, allowing you to map the environment without altering the managed entity. When we perform state changes, we shift to put or patch requests, where the precision of the payload determines the success or failure of the deployment heuristic. Consider the case of deploying a server profile. The integration engine must calculate the resource availability and compatibility constraints before committing to a post action. If the cryptographic baseline, often enforced via session tokens or API keys, does not align with the security policy, the API gateway will terminate the handshake, leaving your deployment script in an indeterminate state. This is where diagnostic logging acts as your primary feedback loop for rapid remediation, distinguishing between a malformed payload and a genuine hardware compatibility exhaustion. Scalability limits and performance tuning in this context involve understanding the overhead of high-frequency polling versus event-driven notifications. In massive data centers, constant polling of API endpoints can introduce unnecessary latency into the control plane, potentially causing resource contention under high-stress conditions. Instead, we advocate for architectures that prioritize batch updates and event-driven triggers, which effectively reduce the compute footprint of your management software. Furthermore, we must address the issue of fault tolerance by implementing circuit breaker patterns within our integration logic. If a connection to an ILO or OneView instance fails, the application should gracefully retry based on defined exponential backoff strategies to avoid overwhelming the resource controller during a recovery phase. This methodical approach to integration ensures that your automated processes retain their integrity even when the underlying data center environment faces unpredictable spikes in operational workload. Predictive failure modeling is the final pillar of a mature REST integration strategy, as it relies on the systematic mining of operational data provided through API telemetry. By regularly querying health indicators and performance metrics, you create a baseline for normal operations that makes anomalous behavior immediately apparent. When the API returns a status code indicative of a potential failure, such as thermal thresholds being crossed or memory error rates climbing, the integration ecosystem should be automated to trigger remediation workflows. These workflows might include migrating virtualized workloads to healthy nodes or reconfiguring network traffic paths to bypass vulnerable components. Effectively, you are codifying the knowledge of experienced infrastructure engineers into software-defined rules, creating a self-healing fabric that minimizes manual touchpoints and maximizes uptime. Integrating these components into your broader hybrid cloud solution guarantees that your automation stays aligned with the rigorous demands of enterprise-grade reliability and compliance standards. See you in the next lecture. Hello, and welcome back to our deep dive into the infrastructure layer of the hybrid cloud environment. In this session, we will focus on the ILO management configuration, a critical component for managing HPE compute resources effectively. The Integrated Lights Out, or ILO, serves as the fundamental out-of-band management processor found on HPE ProLiant servers. By providing a secure, dedicated connection, ILO enables administrators to perform essential lifecycle management tasks even when the host operating system is unreachable or powered down. This architecture is vital for modern data centers because it decouples management traffic from production data traffic, thereby enhancing security and administrative resilience. We must treat ILO not merely as a remote console, but as a sophisticated software-defined control mechanism. Through its dedicated network interface, ILO provides granular access to hardware health, power status, and firmware deployment, which are necessary prerequisites for a stable hybrid cloud integration. When designing for the hybrid cloud, understanding these local management constructs allows for the successful integration of edge compute resources into centralized management planes. To effectively manage ILO at scale, one must understand the interaction between hardware-level controllers and the broader management ecosystem, such as HPE OneView. The configuration of ILO involves establishing cryptographic baselines, which involves securing the management network through TLS protocols and managing security certificates effectively. Failing to enforce these baselines can create significant vulnerabilities, particularly in scenarios where remote access is permitted across site boundaries. Furthermore, API utilization within ILO allows for programmatic management, enabling the automation of configuration tasks across large clusters of servers. By leveraging the ILO RESTful API, engineers can integrate diagnostic telemetry into predictive failure modeling systems. This is particularly relevant when monitoring the environment for performance tuning, as it allows administrators to correlate physical hardware metrics with the performance of cloud-hosted workloads. Resource algorithms and fault tolerance mechanisms are embedded directly into the ILO architecture to ensure system stability under stress. When we configure ILO, we are essentially defining how the server behaves during abnormal conditions, including fan speed control algorithms and power management thresholds. These configurations act as the final line of defense before a potential system failure occurs, contributing to the overall resiliency of the infrastructure. For instance, diagnostic telemetry collected by ILO is indispensable during incident remediation. It provides a detailed ledger of the hardware state prior to a fault, which is essential for root cause analysis. We must be aware of the scalability limits of these management controllers, particularly when managing hundreds of nodes simultaneously, as latency and management queries can indicate configuration drift. Proper deployment heuristics ensure that these management controllers remain responsive, allowing for the rapid deployment of firmware updates and infrastructure templates. Maintaining a rigorous standard for ILO configuration is essential for modern enterprises operating within the hybrid cloud landscape. We have explored the primary mechanisms and architectural requirements that dictate effective management of these controllers. I will see you in the next lecture. Welcome to this chapter on VMware vSphere integration, where we will examine the technical mechanisms required to bridge HPE hardware with mature virtualization stacks. We will focus specifically on the configuration requirements and architectural synergies necessary for deploying resilient hybrid cloud environments. Integrating VMware vSphere into an HPE environment is not merely a matter of installing a hypervisor on a server. It requires a deep understanding of hardware abstraction layers and software-defined control mechanisms. When we talk about integration, we are primarily concerned with how the ESXi host interacts with the underlying silicon root of trust and firmware management components. This interaction is mediated by specific resource algorithms that dictate how compute, storage, and networking resources are allocated across the virtual fabric. You must understand that VMware vSphere relies on consistent hardware compatibility lists, and any deviation from these validated configurations introduces significant risk to lifecycle management. These integration metrics are not arbitrary, but rather calculated constraints designed to ensure that fault tolerance features like high availability or distributed resource scheduler function correctly under heavy loads. If your cryptographic baselines are not perfectly aligned between the hardware ILO layer and the virtual layer, you will quickly find that automated remediation processes fail to execute when an issue arises. A core component of this integration involves the utilization of APIs that allow HPE management tools to communicate directly with the VMware vCenter server. Through these interfaces, we can automate the deployment of virtual machines while simultaneously managing the lifecycle of the host firmware. This is where the concept of condensed configuration matrices becomes relevant, as you are essentially mapping physical server profiles to virtual clusters. When performance tuning becomes necessary, you must rely on diagnostic telemetry gathered from both the physical server sensors and the internal hypervisor performance counters. By analyzing this data, you can develop predictive failure models that allow you to evacuate workloads before a physical component experiences a hard fault. This form of rapid remediation is the gold standard of modern data centers, as it prevents unplanned downtime during peak demand periods. You must also consider the scalability limits, such as the maximum number of VMs per host or the latency thresholds for storage connectivity, which are hard-coded into the integration architecture. Effective lifecycle management within a vSphere environment requires a disciplined approach to firmware baselines and driver distribution. The synergy between HPE ProLiant servers and VMware vSphere is maintained through constant updates that patch security vulnerabilities and optimize resource allocation algorithms. You need to be familiar with how to leverage OneView to push these updates across a cluster without disrupting critical production workloads. This often involves orchestrating vMotion events to move virtual machines to alternate hosts before a scheduled maintenance task takes place on the primary host. The cryptographic baselines, particularly regarding encrypted vMotion and virtual machine encryption, represent the baseline security posture for any enterprise deployment. Failure to maintain these standards can result in data exposure or compromised integrity, which is why compliance auditing within the management console is a mandatory practice for architects. By internalizing these requirements, you ensure that your virtualization layer remains a robust participant in your overall hybrid cloud strategy. See you in the next lecture. Welcome back. In this lesson, we will focus on the technical nuances of Microsoft Hyper-V within the context of your hybrid cloud architecture. Microsoft Hyper-V operates as a Type 1 hypervisor, which means it runs directly on the server hardware rather than on top of a host operating system. This architectural choice is foundational because it dictates how the hypervisor interacts with the physical CPU, memory, and storage controllers. When we deploy Hyper-V in an enterprise environment, especially one leveraging HPE hardware, we need to respect the abstraction layer created by the virtual machine bus. This communication mechanism allows the guest partitions to interact with the hypervisor via BUS, which is critical for performance metrics and resource allocation. Understanding that Hyper-V utilizes a microkernelized design helps explain why it is so effective at isolating partitions while maintaining high throughput for hybrid workloads. You must consider that the parent partition, often called the management operating system, carries the responsibility of device driver management. If the management partition experiences resource exhaustion or driver instability, the entire virtualization host suffers, regardless of how well the individual virtual machines are provisioned. When we analyze the integration of Hyper-V into a hybrid cloud strategy, the focus shifts towards software-defined control and lifecycle management. The hypervisor does not exist in a vacuum. It acts as an endpoint for management tools like HPE OneView, which can orchestrate the underlying ProLiant server hardware. Integration metrics are largely determined by how effectively we map virtual resources to physical compute tiers. For instance, maintaining performance parity in a hybrid setup requires us to define strict resource algorithms. These algorithms govern how the hypervisor schedules threads across physical cores, considering the non-uniform memory access, or NUMA, boundaries of the server. If we ignore these architectural constraints, we risk artificial bottlenecks where virtual machines wait on memory access that is local to another processor socket. This is precisely why we must internalize the configuration matrices associated with your specific server hardware. Deployment heuristics for Hyper-V often center on balancing fault tolerance with scalability limits. We typically approach high availability through failover clustering, which requires a shared storage backend, such as an HPE Alletra array. The diagnostic telemetry provided by Hyper-V's performance counters proves invaluable when we are modeling predictive failure scenarios. We look for patterns in the event logs, specifically those related to hardware abstraction layer errors or VMBus heartbeats, to identify issues before they manifest as downtime. Furthermore, we must address the cryptographic baselines inherent to modern enterprise deployments. Utilizing features like shielded virtual machines helps us secure the boot process and disk content, ensuring that even if physical storage is compromised, the data remains inaccessible without the appropriate fabric keys. These security parameters are non-negotiable in a regulated hybrid infrastructure and demand a rigorous approach to system configuration. Troubleshooting the Hyper-V ecosystem relies on the precision of our diagnostic approach. When we encounter latency spikes in a virtualized container or a standard virtual machine, the first step is to examine the integration services versioning. Discrepancies between the hypervisor version and the installed integration components often lead to suboptimal hardware abstraction performance, which can be difficult to trace without the right telemetry data. We also need to be adept at utilizing PowerShell for rapid remediation and automated deployment tasks. Managing virtual switches and virtual network adapters through scriptable interfaces allows for consistent network traffic management across multiple host nodes. By standardizing these configurations, we move closer to a repeatable deployment model that aligns with the broader goals of our consumption-based IT strategy. Keep these mechanisms in mind as you map out your virtual infrastructure. I look forward to our next session. Welcome back. In this lecture, we are going to explore the fundamental operational mechanics of Kubernetes within the context of hybrid cloud deployments. When we talk about Kubernetes operations, we are essentially discussing the abstraction of hardware resources into a software-defined plane that manages container lifecycles. At the core of these operations, we find the API server, which acts as the central control mechanism for all cluster interactions. When you deploy a workload, you are not merely placing a process on a server. You are interacting with a declarative model, where the cluster constantly reconciles the actual state of your environment against the desired state defined in your manifests. For an HPE specialized environment, this integration often involves mapping these logical pods and controllers to physical ProLiant or Synergy compute resources through specific container storage interfaces and container network interfaces. You must understand that Kubernetes relies on a distributed key value store, typically etcd, to maintain cluster consistency, which places strict requirements on the underlying storage performance and latency. If your etcd latency is high, your entire control plane will experience degradation, leading to reconciliation loops that fail to complete in a timely manner. This, in turn, impacts the lifecycle management of your pods, causing unpredictable behavior during scaling events or node failures. Managing scalability in a hybrid environment requires a deep familiarity with resource algorithms and internal metrics. Unlike traditional virtual machine management, where you allocate fixed blocks of CPU and memory, Kubernetes utilizes a request and limit model that directly influences scheduler behavior and quality of service classes. When you define a container, the scheduler uses the request parameter to determine node placement, while the limit parameter informs the kernel's C groups controller on how to throttle the process if it exceeds its budget. It is a common misconception that setting high limits protects an application. In reality, overcommitting resources across a cluster can lead to node-level resource contention, where the eviction manager starts terminating low-priority pods to preserve the stability of the node. To avoid these scenarios in a professional data center, we rely on diagnostic telemetry that tracks cluster-wide utilization trends rather than simple threshold alerts. You should be looking at metrics such as pod restart counts and pending status durations as primary indicators of underlying architectural constraints rather than just raw CPU usage percentages. Fault tolerance is not an optional feature, but a design prerequisite when running containerized workloads at scale. Kubernetes achieves high availability through health probes, specifically liveness and readiness controls, which provide a feedback loop between the container runtime and the control plane. In a hybrid cloud scenario, you must also account for the latency introduced by external persistent volumes being mounted across a network fabric. This fabric configuration dictates how rapidly a pod can recover from a failover event. If the storage layer cannot detach from the crashed node and reattach to the healthy node in a predictable time frame, the pod stays stuck in a transit state that triggers unnecessary alerts. Furthermore, cryptographic baselines are applied at the communication layer, usually requiring mutual TLS between services to ensure the integrity of the data in transit. As you master these operations, you will find that the most resilient deployments are those that treat their container orchestrators as a black box that responds predictably to failure through automated remediation and intelligent scheduling. Performance tuning within this ecosystem requires a disciplined approach to observed data and predictive failure modeling. We often use daemon sets for logging and monitoring, which sit on every node and collect the diagnostic telemetry necessary for post-mortem analysis. When integrating this with HPE infrastructure, you gain the advantage of firmware-level visibility, which allows you to correlate container-level anomalies with physical hardware interruptions or thermal events. By internalizing these compressed specifications, you ensure that your infrastructure remains alignment with best practices, allowing it to withstand the rigorous stress conditions that modern, globally distributed data centers impose on hybrid cloud solutions. This requires not just knowledge of YAML file structures, but a holistic view of the stack, from the physical silicon root of trust up to the application containers that drive your business logic. See you in the next session. Welcome back. In this session, we will examine the technical mechanics of virtual machine deployment within the context of HPE hybrid cloud environments. When we discuss virtual machine deployment in modern enterprise infrastructures, we are effectively talking about the orchestration of abstraction layers that govern how compute resources are allocated and consumed. Effectively provisioning a virtual machine is not simply a matter of selecting an image and assigning CPU or RAM, but rather understanding how software-defined control mechanisms interact with the physical hardware layer. HPE environments often leverage specific abstractions, such as server profiles and hardware-defined templates, to ensure that the deployment is consistent, repeatable, and compliant with established architectural constraints. We must consider the underlying resource algorithms that dictate host placement, as these algorithms directly influence the distribution of workloads across your compute fabric. Efficient deployment relies on the tight integration between orchestration tools and the hypervisor, ensuring that metadata, storage attachments, and network configurations are propagated correctly across the hybrid cloud ecosystem. One of the most critical aspects of this deployment process involves the constraints imposed by software-defined storage and networking. When you initiate a deployment, the control plane must validate that the target hardware meets the specific compatibility matrices required for the intended workload. If your configuration includes high availability requirements, the deployment mechanism must factor in fault tolerance policies that mandate specific placement heuristics to avoid single points of failure. We look at resource provisioning through the lens of API utilization, as manual intervention rarely scales in enterprise settings. By automating the deployment lifecycle, you reduce the surface area for human error and ensure that cryptographic baselines are applied consistently from the moment a virtual machine is instantiated. This level of rigor is what differentiates a standard virtualization effort from a resilient, production-grade hybrid cloud deployment. Furthermore, we must address the reality of lifecycle management and the diagnostic telemetry captured during the deployment process. Every virtual machine carries a footprint that must be monitored for performance tuning, and the initial deployment parameters define the boundaries of that footprint. When dealing with condensed data environments, understanding the relationship between the guest operating system and the host hardware is essential for predicting potential resource contention. We utilize predictive failure modeling to determine if a specific piece of infrastructure is capable of handling the load associated with new virtual machine instances before the actual deployment occurs. This creates a feedback loop where diagnostic data gathered during operation feeds back into the deployment templates, allowing for iterative improvements. When these deployments fail, your ability to rely on standardized remediation scripts is entirely dependent on how accurately those templates were defined during the architectural phase. Scalability limits often become the primary bottleneck in large-scale virtual machine estates, making it imperative that you understand the performance tuning parameters available at the cluster and host levels. In a hybrid model, workload portability requires that the virtual machine image adheres to formats that can be interpreted across distinct cloud environments without losing critical configuration metadata. This portability is governed by the consistency of the deployment tools, such as the integration between VMware vSphere or Microsoft Hyper-V and the broader HPE infrastructure management stack. You should view the virtual machine deployment not as an isolated task, but as a component of an integrated service delivery pipeline that encompasses everything from hardware, firmware baselines to the application layer. By maintaining a strict adherence to these established software-defined practices, you ensure that the infrastructure remains flexible enough to evolve as business requirements fluctuate. The goal remains the creation of a responsive environment where the deployment of a virtual machine is merely a predictable outcome of a well-defined architectural process. I will see you in our next technical segment. Welcome back to our discussion on infrastructure orchestration, where we turn our attention specifically to container orchestration tools within the hybrid cloud landscape. This chapter will provide the necessary technical rigor to master container lifecycles and architectural scaling within the HPE ecosystem. Container orchestration represents the necessary abstraction layer for managing containerized workloads at scale, moving beyond simple execution to automated deployment, management, and networking. In the context of HPE infrastructure, orchestration tools like Kubernetes are not merely software deployments, but are tightly coupled with the underlying physical hardware to ensure performance consistency and resource efficiency. When we evaluate orchestration, we must consider the control plane as the brain of the operation, responsible for scheduling, health monitoring, and scaling events based on defined metrics. The orchestration layer facilitates the translation of business-level intent into the specific operational states required by the underlying server architectures. By leveraging the physical compute resources provided by platforms like HPE Synergy or ProLiant servers, orchestration tools can achieve high availability across distributed nodes. The fundamental challenge here is managing the state of pods, which are the smallest deployable units, ensuring that their lifecycle aligns with the resource constraints of the host hardware. We must look at resource algorithms and the way these allocators interact with the hardware abstraction layers to prevent bottlenecks during peak compute demands. This interaction necessitates a deep understanding of how container runtimes communicate with the kernel and the specific interfaces provided by the orchestration platform to expose hardware capabilities. Efficient orchestration also involves balancing the ingress and egress traffic, ensuring that the network fabric configuration supports the high bandwidth requirements of distributed containerized applications. One of the most critical aspects of managing orchestration tools is the implementation of effective lifecycle management and fault-tolerant strategies. In an enterprise environment, we cannot rely on manual remediation. We must utilize the diagnostic telemetry provided by the orchestration suite to trigger automated recovery processes when failure thresholds are breached. Predictive failure modeling allows us to shift from a reactive stance to a proactive posture, where the orchestration engine shifts workloads away from nodes showing signs of instability. You need to internalize the configuration matrices that dictate how replicas are distributed across separate physical chassis to satisfy the requirement for hardware-level fault domain isolation. Furthermore, the integration of API utilization within these tools is what allows for the seamless scaling of infrastructure components in response to application telemetry data. When we discuss scalability limits, we are referencing the maximum number of pods, services, and nodes that an orchestration control plane can manage before latency affects the consensus mechanism. Understanding cryptographic baselines is equally vital, as securing the communication channels within the container cluster is an absolute requirement for meeting modern enterprise security standards. You must ensure that the orchestration tools are configured to enforce zero-trust principles, validating every service-to-service interaction through robust identity management and encrypted protocols. Finally, the performance tuning phase involves identifying the specific resource algorithms that govern CPU and memory reservations, which directly dictates how workloads compete for the physical capacity of the underlying hybrid cloud fabric. Consider these technical parameters as the building blocks for any resilient infrastructure deployment you might encounter in the field. I look forward to seeing you in the next lecture. Welcome back. Today, we are shifting our focus toward the architectural requirements and operational mechanics that enable true hybrid workload portability within modern data center environments. Hybrid workload portability is not merely the ability to migrate a virtual machine from an on-premises host to a public cloud provider. Instead, it represents a comprehensive architectural strategy where performance, security policies, and resource constraints remain consistent across disparate environments. To achieve this, we must consider the software-defined control mechanisms that decouple the workload from the underlying physical hardware. When you look at HPE solutions, this often involves leveraging abstraction layers that allow infrastructure to be treated as code. By utilizing standardized APIs to manage these resources, administrators can ensure that a service profiled for a high-performance environment carries the same configuration requirements wherever it lands. This abstraction effectively hides the complexity of underlying hardware incompatibilities that would otherwise break service deployment. The foundation of successful portability lies in the utilization of mature lifecycle management frameworks and consistent API utilization. We often encounter technical barriers when attempting to move workloads because of varying resource availability and hypervisor configurations. To mitigate this risk, enterprise architects focus on building deployment heuristics that evaluate the target environment's capacity before any migration is initiated. These algorithms monitor available CPU cycles, memory overhead, and storage throughput to ensure the target can maintain the workload service level agreement. If the diagnostic telemetry indicates that the destination environment lacks the necessary performance baseline, the automation framework should intercept the request and prevent an unstable deployment. This predictive approach is essential for maintaining resilient infrastructures, especially when dealing with high-demand production applications that cannot tolerate latency fluctuations. Effective portability also requires a deep understanding of cryptographic baselines and internal security constraints. As a workload moves across boundaries, the integrity of its data and its access control policies must remain immutable. This is why software-defined security architectures, which rely on hardware-validated roots of trust, are so critical to the ecosystem. You have to ensure that the cryptographic identity of the workload is not tied to a specific physical server, but rather exists as a portable asset that the infrastructure can verify regardless of location. When you design your deployment templates, think about how you will inject these security secrets during the provisioning process. Integrating these security parameters into your infrastructure orchestration ensures that you are providing a defense-in-depth posture that follows the workload, rather than forcing the workload to comply with the local security settings of the host. Finally, we must address the reality of hardware compatibility and the impact of software-defined control on overall scalability. At scale, manual intervention is simply not an option, which is why we rely on resource algorithms to manage workload placement based on real-time performance tuning metrics. These algorithms analyze the state of the data center and determine the optimal placement for containers or virtual machines based on predefined constraints. Troubleshooting these automated transitions requires a comprehensive grasp of diagnostic telemetry, where we interpret system logs to predict and resolve failures before they impact the user. By internalizing these requirements, you position yourself to design systems that are not just functioning today, but that are robust enough to survive the rigorous stress tests of the modern global enterprise. I will see you in the next lecture. Hello. Welcome to this session on assessing enterprise workloads. In this chapter, we will examine the technical requirements and analytical frameworks necessary to effectively evaluate and integrate complex enterprise environments into a hybrid cloud ecosystem. To build a resilient hybrid cloud strategy, we must first master the art of assessing enterprise workloads with precision. This course is designed to take you from a basic understanding of cloud concepts to becoming an expert in architectural assessments, ensuring you pass the HPE0-V25 exam with confidence. You will learn to navigate the complexities of data migration, resource optimization, and technical performance tuning. By the end of this journey, you will possess the specialized knowledge required to lead enterprise-level deployments and drive real-world value for your organization. Selecting this course is a direct investment in your professional capability to master the modern data center. Assessing enterprise workloads requires a shift from viewing infrastructure as static hardware to viewing it as a dynamic, software-defined entity that must meet specific business outcomes. When we evaluate an existing environment, the primary goal is to map operational requirements against the capabilities of HPE hybrid cloud solutions like GreenLake or ProLiant systems. We start by gathering data on performance metrics, but raw data is rarely enough to make an informed architectural decision. Instead, we look at the interaction between resource consumption, application latency, and the underlying storage and network fabrics that support them. This process involves a deep look at architectural constraints that often limit how we scale or migrate specific workloads. For example, legacy applications might have specific hardware dependencies that prevent them from moving immediately into a containerized environment, requiring a methodical decomposition of the application stack. We prioritize understanding these throughput limits and latency sensitivities to ensure the target environment does not become a bottleneck during or after integration. Integration metrics serve as the backbone for assessing workload readiness and determining whether a move to a hybrid model is justified. We must analyze how software-defined control mechanisms operate within the infrastructure stack, specifically looking at how APIs interact with existing compute and storage resources. Hardware compatibility is not merely a checkbox. It is a fundamental constraint that dictates how effectively workloads can be orchestrated across hybrid boundaries. Furthermore, we must account for cryptographic baselines when dealing with sensitive enterprise data, as shifting a workload requires maintaining the same security posture in the new cloud environment. These baselines act as a security contract that remains valid regardless of whether the physical hardware sits in an on-premises rack or a managed cloud service. When you evaluate these components, consider the lifecycle management of each workload and how it aligns with the expected lifecycle of the supporting infrastructure. A well-assessed workload is one where the data intensity, security requirements, and scalability needs are fully transparent and manageable through centralized software-defined controllers. Resource algorithms and fault-tolerance strategies are equally vital when we move beyond simple capacity planning into the realm of active enterprise workload management. We measure the success of an assessment by how well we can predict system behavior under stress, which is where telemetry and diagnostic monitoring come into play. Modern data centers utilize predictive failure modeling to minimize downtime, and our assessment methodology must integrate with these mechanisms to ensure total operational continuity. When you perform these assessments, you are essentially creating a blueprint for the future state of the infrastructure that prioritizes resilience and performance predictability. We look at API utilization trends to understand if the current management layer can handle the load of automated scaling, or if additional orchestration tools are necessary. Effective workload management is proactive rather than reactive, utilizing robust data points to anticipate demand spikes long before they impact the end-user experience. By internalizing these technical requirements, you establish a standard of excellence that keeps infrastructure operating at peak efficiency under the most rigorous conditions. I will see you in our next session. Hello, everyone. Let us examine the intricacies of quantifying returns within a hybrid infrastructure. In this section, we will explore the essential metrics and decision-making frameworks required to perform effective cloud ROI comparisons. When we approach the challenge of calculating return on investment for a hybrid cloud deployment, we must move beyond simple capital expenditure analysis. The objective is to evaluate the total cost of ownership by balancing the agility of public cloud services against the predictable performance characteristics of on-premises hardware. You need to account for hidden costs such as data egress fees, latency-related productivity losses, and the overhead associated with managing heterogeneous environments. A robust ROI model incorporates the lifecycle management of compute resources, where software-defined control mechanisms allow for more precise resource allocation. By leveraging HPE GreenLake, for instance, organizations can transition from a rigid procurement cycle to a consumption-based model that aligns expenditure directly with actual workload utilization. Integration metrics serve as the backbone for these comparisons, particularly when we assess hybrid cloud ecosystems that combine legacy systems with modern cloud-native architectures. You should focus on deployment heuristics that track the time required to provision services and the resource algorithms that determine when to scale specific workloads. If an application exhibits volatile demand patterns, the ROI calculation must heavily weight the scalability limits of the physical hardware versus the elastic capabilities offered by cloud providers. Furthermore, architectural constraints often dictate the feasibility of a migration, as some workloads may face cryptographic baselines that necessitate local residency for security compliance. These constraints essentially act as multipliers or divisors in your financial model, impacting the overall efficiency of the infrastructure investment. Performance tuning and diagnostic telemetry provide the data points necessary to refine your ROI models over time. Predictive failure modeling within the HPE ecosystem enables you to quantify the financial impact of downtime, which is a critical variable in any enterprise deployment assessment. When you integrate these findings into your financial reports, you justify the initial higher costs of resilient hardware through the avoidance of expensive service disruptions. Additionally, the role of API utilization in automating management tasks should be factored into your operational expenditure reduction. By automating routine maintenance and firmware updates, you reduce the human labor required to maintain the system, which directly improves the bottom line ROI when comparing managed cloud tiers against internal administrative costs. Understanding the scalability limits and fault tolerance mechanisms provides the clarity needed to make informed long-term infrastructure decisions. You are not simply choosing between a server and a virtual instance. You are orchestrating a complex set of variables that define the financial health of the data center. By maintaining a deep focus on these technical parameters, you ensure that the hybrid cloud environment remains economically viable under the rigorous stress conditions typical of global enterprise operations. This disciplined approach to financial and technical integration ensures that you can justify technology spend to stakeholders while maintaining the high-performance standards required by the business. You now possess the analytical perspective needed to evaluate these complex financial scenarios with precision and technical rigor. I will see you in the next lecture. Welcome to this exploration of the Silicon Root of Trust, a fundamental security paradigm within the HPE server ecosystem. In this chapter, we will dissect the architectural mechanics that ensure our infrastructure remains immutable and trustworthy from the moment of power on. The Silicon Root of Trust functions as an immutable fingerprint etched directly into the HPE ILO silicon, serving as a foundational security anchor that cannot be altered or bypassed by conventional software vulnerabilities. Unlike legacy approaches that rely on software-based BIOS verification, this hardware-centric architecture validates the integrity of the firmware before the processor ever accesses a single instruction from the system memory. When you initiate a server boot, the silicon automatically initiates a cryptographic handshake that verifies the immutable code stored within the chip itself. If the firmware is found to be compromised or tampered with, the system gracefully halts the boot process, effectively preventing the execution of malicious code at the most privileged layer of the hardware stack. This mechanism is not merely an optional security feature, but an architectural constraint that forms the backbone of modern enterprise security baselines. By anchoring trust in the silicon, HPE effectively mitigates risks associated with supply chain attacks or unauthorized firmware modifications that could otherwise compromise the entire hybrid cloud fabric. Moving into the deployment heuristics, we must understand how this trust chain interacts with the broader software-defined control mechanisms that characterize HPE GreenLake and similar hybrid environments. The Silicon Root of Trust provides a cryptographic foundation that allows management tools like HPE OneView to maintain a verifiable audit trail of system health and authenticity. When we look at lifecycle management, the interaction between the silicon layer and the OS-level security features requires a deep comprehension of how cryptographic keys are managed across the infrastructure. We often encounter complex configuration matrices where firmware, drivers, and management layers must align to maintain the trusted state without restricting the scalability or flexibility of our workloads. Integration metrics are essentially derived from the ability of the system to perform rapid, autonomous remediation should the silicon detect a mismatch during a routine firmware update cycle. This rapid remediation capability underscores the fault tolerance inherent in the design, ensuring that even if a firmware update is corrupted, the system can revert to a known good state without human intervention. From a performance and scalability perspective, the overhead introduced by these cryptographic baselines is negligible, yet the implications for resource algorithms are profound. Modern data centers require high-speed provisioning, and the Silicon Root of Trust speeds up the validation process by offloading complex cryptographic operations to dedicated hardware engines within the ILO subsystem. When we discuss scalability limits, we are essentially looking at the bandwidth of the management fabric and how effectively it can communicate with these secure silicon endpoints during large-scale server rollouts. Diagnostic telemetry is another critical pillar here, as the silicon provides specific error codes and status indicators that allow system administrators to differentiate between genuine hardware failures and malicious integrity breaches. Predictive failure modeling leverages this telemetry data to flag potential issues before they translate into downtime, providing a layer of proactive security that is essential for resilient infrastructures. As you refine your knowledge for the certification exam, keep in mind that the effectiveness of this security model is entirely dependent on the rigor with which we apply firmware baselines across our entire compute fleet globally. See you in the next lecture. Welcome to this chapter on Zero Trust Architectures. We will explore how to secure hybrid cloud environments by assuming no implicit trust, regardless of where a user or resource originates. Zero Trust is not merely a product or a single piece of software. It is a strategic framework designed to eliminate the concept of perimeter-based security in favor of granular, policy-driven verification. In a traditional network model, we often operate under the assumption that anything inside the corporate firewall is inherently safe, which is a dangerous fallacy in the modern hybrid cloud era. By adopting Zero Trust, we shift our focus to individual identities, workloads, and devices, requiring continuous authentication and authorization for every access request. This approach assumes that the network is always compromised, requiring us to monitor, log, and inspect all traffic, both north-south and east-west. Within the context of HPE hardware and software-defined solutions, this translates into leveraging integrated security features that act as the foundation for these policies. When you build an enterprise infrastructure, you must consider how each component, from the server firmware to the API layer, contributes to a collective posture of verification and minimal privilege. At the core of implementing this architecture lies the mechanism of identity-powered access control, where cryptographic baselines serve as our primary defense. We must ensure that only authenticated identities, whether human operators or machine-to-machine processes, can interact with sensitive resources. This is particularly relevant when dealing with hybrid clouds, where workloads might span between on-premises ProLiant servers and public cloud instances. To enforce this, we utilize hardware-based roots of trust that provide an immutable identity to the compute node, ensuring that the software stack has not been tampered with before it even begins to boot. Furthermore, we must address the management of API calls, which are the arteries of modern data center orchestration. Every request made through a REST API to your storage or compute controllers must be authenticated with the same level of rigor as a manual login, ensuring that the configuration management plane remains untainted by unauthorized commands. When we translate these concepts into architectural constraints, we find that scalability and performance often conflict with strict security policies. A zero-trust model requires inspecting traffic and verifying identities at every hop, which can introduce latency if not properly balanced with efficient resource algorithms. You need to understand the performance tuning parameters available within your software-defined network fabric to ensure that encryption overhead, while necessary, does not degrade the efficiency of your hybrid workloads. During a potential breach or a misconfiguration event, diagnostic telemetry becomes your most valuable asset for rapid remediation. By internalizing predictive failure modeling, you can identify anomalies and traffic patterns that might indicate a lateral movement attempt within the network. This capability allows you to transition your security model from a reactive stance to a proactive one, effectively isolating suspicious segments before they impact the broader enterprise ecosystem. Resilient infrastructures in modern data centers require deep integration between the hardware layer and the management plane. We rely on the concept of least privilege, which, in technical terms, means that each workload should only be able to communicate with the specific services it requires to fulfill its function. When configuring your compute and storage fabrics, you should design them to segment traffic automatically, preventing the sprawl of unauthorized or unnecessary connections. Lifecycle management of these security policies is equally vital. A security is never a static configuration. It evolves as your infrastructure scales and changes. Whether you are managing containerized workloads or standard virtual machines, the policy must follow the asset rather than remaining tied to a specific physical server or network switch port. By mastering these compressed specifications, you ensure that your deployment remains robust even under the high-stress conditions characterized by evolving global threat landscapes. I look forward to continuing our path towards certification in the next segment. Welcome back. And today we turn our attention to the critical task of interpreting system logs within the context of HPE hybrid cloud solutions. By the end of this session, you will grasp how to navigate diagnostic telemetry and architectural constraints to ensure infrastructure resilience. In any complex hybrid environment, system logs serve as our primary source of truth, yet they are rarely human-readable in their raw state. We are dealing with massive volumes of condensed data streams generated by hardware controllers, storage fabrics, and software-defined management layers. When we look at HPE infrastructure, specifically the diagnostic telemetry pouring out of components like ILO or OneView, the challenge is not just capturing the data, but understanding the semantics of the underlying resource algorithms. We must learn to differentiate between noise, which is expected telemetry, and actual fault indicators that require immediate remediation. If you fail to correlate these events across the hybrid stack, you end up treating symptoms while the root cause remains buried in a mismatched configuration matrix. Effective interpretation begins with understanding how deployment heuristics influence logging behavior across various hardware generations. For instance, the way a ProLiant Gen11 server reports power fluctuation telemetry differs significantly from older architectures because of the increased granularity in the software-defined control mechanisms. You have to account for these architectural constraints when setting your baselines, as a standard threshold for latency might be perfectly acceptable in one service model, but represent a critical failure in another. The goal is to move from reactive log parsing to a proactive state where you recognize patterns before they trigger a system-wide breach. This requires a deep comprehension of how API utilization facilitates the collection of log data into centralized monitoring tools. When we examine the lifecycle management of these systems, we inevitably encounter the intersection of cryptographic baselines and system integrity logs. A change in the security posture of an appliance or an unauthorized attempt to modify firmware baselines will be recorded in the security events log, provided those logs are correctly configured and ingested. Many candidates overlook the fact that logging is not just a debugging tool, it is a fundamental component of a zero-trust architecture. By evaluating these logs through the lens of identity and access management, we can identify anomalies in resource consumption that suggest a broader security compromise. You must understand which log levels provide the necessary visibility into authenticated versus unauthenticated traffic to maintain enterprise-grade security. Scalability limits also manifest through specific log markers, often appearing as subtle performance degradation patterns rather than sudden crashes. When we look at resource algorithms, we often see that as a cluster approaches its capacity threshold, the system begins to produce log entries regarding queue depth or fabric contention. If you're not familiar with the baseline telemetry for your specific deployment, you might mistake a performance bottleneck for a hardware failure. Predictive failure modeling relies on our ability to distinguish these patterns from transient network jitters or standard load spikes. Keeping a clean, actionable log profile is therefore essential for rapid remediation in environments that demand high availability under rigorous stress conditions. Finally, we must consider how these logs integrate into the broader hybrid cloud ecosystem. The interoperability between on-premises diagnostic data and cloud-based management platforms depends entirely on the standardized format of the logs being exported. We use API utilization to bridge these gaps, ensuring that the telemetry gathered locally can be analyzed against global datasets to identify systemic issues. This level of integration is what separates a resilient enterprise architecture from a collection of siloed components. When you master the art of interpreting these logs, you gain the ability to perform precise performance tuning and ensure that your deployment adheres to the vendor's best practices. This is the cornerstone of effectively maintaining complex, large-scale hybrid systems. I will see you in the next session. Hello, welcome back. Today we turn our attention to HPE InfoSight and its role in predictive analytics within hybrid cloud environments. HPE InfoSight serves as the core intelligence engine within the HPE ecosystem, moving beyond traditional reactive monitoring into the realm of predictive analytics. It functions by collecting vast quantities of diagnostic telemetry from hardware and software components across the data center, including servers, storage arrays, and networking fabric. This data is not merely stored but processed through cloud-based machine learning algorithms that identify patterns and anomalies invisible to the human eye. By analyzing performance trends and health indicators, InfoSight models potential failure scenarios before they impact production workloads. This is a significant shift in infrastructure management strategy, as it eliminates the reliance on standard threshold alerts that often occur after a failure condition is already in progress. The architecture relies on an always-on connection to the cloud portal where the gathered telemetry is correlated against the experiences of a massive global install base. Understanding the underlying mechanics of this platform requires a focus on how it handles diagnostic telemetry and resource algorithms to manage modern data centers. The system employs complex heuristics to distinguish between benign performance fluctuations and indicators of genuine component degradation or failure. For hybrid cloud integration, the platform effectively correlates data from heterogeneous sources, allowing administrators to maintain visibility across both on-premises assets and cloud-native services. Deployment heuristics must be strictly followed to ensure that telemetry streams are not throttled or blocked by local security proxies or firewall policies. Within this framework, lifecycle management is automated through the continuous feedback loop provided by the Predictive engine, which suggests firmware updates or configuration changes based on known compatibility matrices. You are effectively shifting from managing individual devices to orchestrating a resilient ecosystem that proactively resolves potential bottlenecks. In terms of performance tuning and scalability limits, InfoSight provides specific insights that allow for granular optimization of resource allocation. It identifies underutilized or over-provisioned virtual machines and storage volumes, providing actionable recommendations to reclaim capacity or improve throughput. These recommendations are based on historical performance data and comparative analysis against thousands of similar deployments within the global HPE community. Furthermore, the cryptographic baselines utilized during data transmission ensure that all diagnostic information remains secure while in transit to the cloud. Fault tolerance is inherently improved as the system can model the impact of a controller failure or a disk depletion event before the physical hardware encounters a critical status. Troubleshooting then moves from a guessing game involving disparate system logs to a targeted, rapid remediation process, guided by the platform's precise predictions. When considering architectural constraints, administrators must remain vigilant about the specific software-defined control mechanisms that interface with the platform. These mechanisms allow for an automated response to certain identified risks, essentially acting as an extension of the administrative team. However, the system is designed to provide recommendations for the administrator to review and approve, maintaining the necessary control over the production environment. You must familiarize yourself with the nuances of these alerts, as distinguishing between a high-priority hardware failure alert and a suggestion for load balancing capacity is critical for efficient data center operations. The platform effectively abstracts the complexity of data center management, allowing you to focus on strategic initiatives rather than daily firefighting of hardware anomalies. Successful implementation depends on the completeness of the telemetry data being transmitted, which necessitates robust, stable network connectivity between your local infrastructure and the InfoSight cloud portals. I look forward to our next discussion. Welcome back. In this final session, we synthesize the hybrid cloud architectural patterns into our ultimate operational baseline. Throughout this curriculum, we have carefully deconstructed the individual components that comprise the HPE hybrid cloud stack, ranging from granular compute architectures to the abstract layers of software-defined networking and security. As we reach the conclusion of our prep, it is essential to view these systems not as isolated silos, but as a unified, cohesive ecosystem that dictates the life cycle of enterprise data. We began by establishing the fundamental strategy behind GreenLake and consumption-based IT, which serve as the financial and structural pillars for modern infrastructure. By transitioning into the physical realities of ProLiant Gen11 hardware and the orchestration power of HPE OneView, we moved from abstract strategy toward the actual deployment heuristics that define daily operations. Our exploration of storage fabrics and Aruba-based networking ensured that we understand the conduits through which data flows, while our deep dive into cryptographic baselines and silicon root of trust confirmed that security is an inherent property of the hardware rather than an auxiliary patch. Now, as we consolidate these concepts, the goal is to develop an intuitive grasp on the scalability limits and performance metrics that characterize a resilient data center deployment under stress. To master these final objectives, one must appreciate the diagnostic telemetry that informs our predictive failure modeling, as this allows for rapid remediation before an issue propagates throughout the fabric. We have looked extensively at how API utilization, specifically through REST interfaces, permits the automation of server profiles and firmware baselines, effectively removing human error from the lifecycle management equation. This integration is what makes software-defined control mechanisms so powerful. They abstract away the underlying complexity, allowing administrators to enforce deployment standards across hybrid and multi-cloud environments consistently. When you consider the resource algorithms required for efficient workload portability between vSphere environments and containerized Kubernetes clusters, you begin to see the architecture as a set of constraints that must be balanced for optimal performance. These constraints, including memory pressure, latency and storage backplanes, and the overhead introduced by encryption, are the variables you will be expected to tune during rigorous deployment scenarios. Maintaining alignment with these best practices ensures that the resulting infrastructure is not just functional, but optimized for the high availability requirements inherent in global enterprise scale. As you prepare for the final certification attempt, remember that the exam evaluates your ability to make trade-offs within these architectural constraints, rather than just memorizing static configuration matrices. You must synthesize the knowledge of how InfoSight's predictive analytics influence your capacity planning, and how that shifts the economic burden of consumption-based models. Every piece of telemetry we have analyzed serves a purpose, whether it is confirming the health of a RAID array within an Alletra system, or verifying the integrity of a boot sequence through the silicon root of trust. Your success relies on your capacity to apply these technical parameters fluidly, transitioning from high-level strategic planning to the low-level remediation of fabric-level events. By internalizing these methodologies, you ensure that your deployment decisions remain grounded in the reality of modern data center constraints. You now possess the analytical foundation required to troubleshoot effectively and optimize for long-term operational sustainability. I wish you the very best of luck with your upcoming exam.